Good morning, everybody, or good afternoon, or potentially good evening. Anyway, this is a video presentation on industrial mixing, multi-phase processing. Based upon, my name's Gary Tatterson with Chemical Engineering Department. Anyway, it's based upon my 4 books. First one is fluid mixing, gas dispersion. The other one is scale up and design. Third one is process design, process scale up and design. And the fourth, scale up, business of scale up. All available on Amazon. And they make very good Christmas gifts, perhaps. Let's talk a little bit about mixing and general aspects of mixing. In the olden days, when chemical engineering was relatively new, mixing and contacting was part of the original 4 areas: fluid mechanics, heat transfer, mass transfer, and mixing. Mixing and contacting was a very important area. It still is a very important area. But in the scheme of things, it was dropped from them. So today we have fluid mechanics, heat transfer, mass transfer. Unfortunately, or fortunately, contacting is needed for most all processes. Chemical reactions, for example, require mixing. And there's many mixing-dependent processes. So we can go, et cetera, et cetera, et cetera, and the fact that mixing is very important. However, mixing is not very well understood or poorly understood. Industry is highly empirical. Information is limited and hard to understand in a practical sense. Okay. You can say this thing about, you can say such statements about like that about most everything. The cost of ineffective mixing is very high. Okay. I ran a 1 gig or one consulting job I had. They had an 18-hour cycle time. In that 18-hour cycle time, there was 2 powder additions to a liquid. And after they added the powder, they had lumps. So it took 12 hours, or 8 or 10 hours to get rid of those lumps. And once they got rid of those lumps, further on down in the procedure, they added some more powder and made lumps again, and took 4 hours to get rid of those lumps. So overall, you had a substantial time created in getting rid of lumps. And the whole concept here is you don't make the lumps in the first place. You figure you're making a powder addition. You get the right equipment for the job. And basically, you feed the particles in such that there's no way they can form lumps. So, excuse me, the company recognized this. They also recognized the fact that they had to change their procedures and phase in these methods for adding powder to a liquid without lumps. And it took them about 2 years to do that. I find it very astonishing. But they reduced their cycle time from 18 hours down to 4 hours or 6 hours or so. And this is a major product for those chaps. But so they essentially, tripled production. They went from 18 to 6 in batch time, right? It's a factor of 3 in production. So there's many examples out there where improved mixing performance can mean a substantial increase in profits. I'm assuming, excuse me, the production here with these 18-hour material, when it took it down to 6 or 4 hours, the profits went up factor of 3 as well. Potential economic costs and losses, well, you can have, due to improper mixing or poor mixing, loss of capital investment, losses in production and quality, increased downstream separation costs, and increased safety and environmental costs. Initial example of initial capital investment being lost: major chemical company on the Gulf Coast built this reactor. I think back in the 1966 era, spent $25 million in the construction of that plant or that reactor system. And they couldn't get the solids off the bottom, the tank bottom, for some reason. Well, solids is a problem phase. And they couldn't get the solids off the tank bottom, so they essentially built the plant in 66 and 67. They took down the plant. Example of loss in capital equipment. Loss in production and quality. I point to this situation up here. You have poor mixing in 18-hour cycles due to lumps being formed. Downstream separation costs, yes. If you don't mix properly, you won't react properly. You'll form byproducts or other reactions will take place. And as a result, you have separation problems. Increased safety and environmental costs. Well, the longer you run a process, the more likely there'll be a safety issue. So the less processing time, the better. That reduces safety problems. So the resolution of a mixing problem or contacting problem, you need continuing education. That's very important. You need the development of a proper perspective, and you need the application of fundamentals. Right? These are three important areas in which you can certainly benefit. I assure you, continuing education is extremely important. Mixing has a wide range of variations and many problems exist, typically in multi-phase processing, different volume fractions. These are typically notorious in getting the process right. Then you have rheology of the various phases. You're also involved with the process energies that are there, energy level, power levels, and our buddy different flow regimes. Typically, you have flow regimes that make money, and then you have flow regimes that don't make you any money. And of course, we have our academic items of boundary and initial conditions. So when you have this variation due to the lack of knowledge or information, every process eventually becomes a special case. Now, that's counterintuitive, right? You want to have generality. But no, indeed, everything is a special case. Engineering situation, well, fundamentals are limited as applied to the process. The process is not well understood. You have CFD. CFD is fantastic. Don't get me wrong. I'm a great believer in CFD. But you can use CFD to understand your process. That's true. But you can calculate a whole bunch of stuff that you can't measure. And actually, what you do with those calculations is the question. You have so much information, don't know which is important, which is not. Anyway, I used to say that the models are rudimentary. Maybe they're not that bad anymore. I would contend that the success ratio of modeling is about 40%, right? 40%. The average weather forecast, I don't know if you've tracked the weather forecast or not, but 40%, or you take a look at a superstar baseball player batting 300, right? 1 out of 3. So even the best of the best, considering how much time and effort has been spent in predicting the weather and the computational capabilities, and they're only coming up with 40%. So process knowledge is needed, okay? And one of the ways of gaining knowledge is CFD. The other way is you go out and study it experimentally. And hopefully you go beyond knowledge and reach a level of understanding. Process understanding is necessary or needed. The bottom line is like anything else, you want to get the right equipment for the job. You want to get the right methods for the job, right? So it's the right equipment, right methods. And hopefully the best designs are based upon engineering knowledge and understanding. Okay. Now, this has given rise to process-specific mixing designs. They have emerged and are quite beneficial in increasing production or profits. Effective at accomplishing the task, objectives over and above the standard designs, improved process performance is likely. Process-specific design should be encouraged. Okay. What this is directed at is you have the concept out there of geometrically similar systems. Well, using geometrically similar systems, what you do is fall into a trap. Okay. And geometric similarity is a trap. Okay. Basically, you look at design. There's two major elements to a design. One is energy level or energy input or operating conditions. So that's one group of things. The other group is geometry. Geometry is very key in design. In fact, design effort to determine the proper design is very, very important. So if you're looking for a proper geometry, then you cannot use geometric similarity. If you use geometric similarity, you have basically cut out a major design variable by fixing the geometry. Anyway, geometric similarity is taught everywhere. Okay, in the undergraduate program and all the fluids courses, you have geometric similarity, dynamic similarity, kinetic similarity. Now, being in this area for 50 years or so, I would not emphasize. Well, I would emphasize the changes in geometry. Instead of fixing geometry, change it. Examples of this, Smith impeller and gas dispersion. This is hollow cone, excuse me, not hollow cone. This is, we'll show you the geometry a little later. Fluid foil impellers and blending operations, that's kind of old, but it's still a new example of a change in geometry. Double helical ribbon with bottom scrapers for mixing, viscous mixing. Maybe a cone bottom where you have varying liquid heights. You have impeller in the tank bottom, very important for solid suspension. Solid suspension is actually a bottom process. So here we more or less have some standard geometries. The first off, you should recognize you have laminar geometries and then you have turbulent geometries, the first thing. Second thing is the laminar geometries might be referred to as full tank. And this one in particular, it looks pretty here, but I would make a few design changes on it. First off, I would remove these arms coming off the impeller. So I would make it so that I can come in with measurement probes anywhere on the interior. Then I would mount the helix on ribbons. So I would put helical ribbon impeller mounted on an anchor impeller. That way I would have good surface renewal at the walls. I would put a bottom scraper in here, and that would be the design I would go with. This is almost a universal mixer. That means it mixes in the laminar regime, transition regime, and the turbulent regime as well. I wouldn't necessarily, this is a good mixer. Okay, I wouldn't necessarily use it because the screw is somewhat cumbersome. Then I would come down here. So we got one geometry that really is basically maybe a universal mixer. Handles laminar, turbulent, and the transition regime, which we'll show you later. Down here we have the standard turbulent geometries, which we could possibly call the standard mistakes. Okay, in the industry, in academic research, the liquid level never changes. Okay, so typically you would not worry about liquid level, but in industry, liquid level is dropping or rising all the time. And when the liquid level drops below the impeller, you lose agitation. And when you lose agitation, you can create a whole bunch of problems here. So, settling, all kinds of problems when you lose agitation. So what might be important is you put a cone bottom on here, You have an impeller going all the way to the bottom of the tank, or a tickler impeller, to provide agitation no matter what liquid level it is. In fact, this could possibly, impeller could be okay. Then I would add another impeller here at the bottom to make sure that you take care of the dead zone at the bottom. Same thing applies to this one, pitch blade. Here you have radial flow, here you have axial flow. And this is excellent because you have a strong wall flow for heat transfer occurring. You also, again, put a cone bottom, put the impeller all the way to the tank bottom, and we'll show you a cone bottom a little later. Now, basically, for turbulent mixers, you have the three biggies right here: propeller, hydrofoil, and pitch blade. Now, all these are good mixers. The hydrofoil looks to be quite strange, but it's quite effective. For example, if you were using a pitch blade turbine, you could change it out and replace it with a hydrofoil. And the hydrofoil could possibly, if it's a large tank, reduce your electricity bill by $40,000. So I don't know if that pays for changing out. That's per year. Up here we have pointed blade impeller. I don't know who would use this. It's often advertised as a high shear impeller. Okay, we can talk about shear a little bit later. Then the problem with radial flow impellers is they tend to stratify the tank. Say I had this one, and then I had another one up here, and I would eventually stratify the tank. Okay, and that's not necessarily good for processing. Okay, I have here a sawtooth impeller. These are often bent up and bent down, the teeth. And when it's bent up or bent down, it's called a cow's impeller. Very useful impeller, right, for dispersion. Now here you have a simple disc. Now what's interesting about this simple disc is it's spinning around. It goes at very high RPMs, right? And it will have curls of vortices all along here. If you go look, this is standard rotating electrode and electrolysis stuff research. And they are able to predict the roll vortices that form on this rotating disc, and top and bottom, right? And what happens is these vortices are all the same. So you've got a substantial uniformity here in the flow. And as a liquid drop comes through those vortices and gets broken up, by the way, vortices will break up drops, you have very good drop uniformity. Since it's the same flow field no matter what, the material sees the same flow field producing the same drop size. Anyway, we also have the old disc style turbine. Basically, you don't want to use this impeller. This is much like a radial flow impeller, but this disc here is a baffle. It's a disc, but it's actually a baffle as well. Gas comes mainly used for, say, gas dispersion. You bubble gas below it, and the gas then goes out to trailing vortices off the blades. Okay. And later, Smith came along and curved these blades. Okay. Well, let's be more accurate about that. Smith's a great guy. I like him a lot. And Van Riet is also a great guy. I like him a lot. They were very nice people, or are nice people. And they had a whole bank of undergraduate / beginning graduate students working for them, 30 or 40. And they were studying all kinds of different effects. And they basically cut a piece of pipe in half and mounted the pipe sections on the blade. And that way you give you a curved blade rotating forward and backward. So now the gas comes bubbling up and goes out to a curved blade. And we'll get at that a little later here, discuss it a little later. So that gives rise to what I call the Smith impeller. And there's a whole bunch of other impellers that sort of mimic this. Here we have the right mounting. It's cupped in the direction of rotation. So it's cupped like this in the direction of rotation. And this is the correct mounting. Now then, if you have some your maintenance people in the tank mounting this thing, right, as I did for a major company we were talking about, they replaced their replaced their Rushton impeller with a Smith impeller. And the people mounting the impeller just said, this doesn't look right. It just simply doesn't look right. So then they mounted the impeller blades like this, cupped. Okay, the leading curvature is in the direction of rotation. This is a wrong mounting. So this is one time that the direction of rotation really does matter if you get it wrong. If it's a single phase motor, all you got to do is change the leads to redirect the direction of rotation. So this is the correct mounting, and this is the wrong mounting. I was in my consulting, I said, basically, I was sitting there, I was laying there at night thinking about this problem, and I said, look, these guys are going to mount the impeller wrong. I mean, the people, they're going to look at this and say, this just doesn't look right, and they'll put this in. So I called up the chap at the company. I said, look, you need to go check to see if they mounted the impeller correctly. And lo and behold, they mounted it wrong, right? So you got to mount it in the right direction. We'll talk about why a little later. Then you can have all kinds of swept back type geometries, basically pitch blades, swept back or flat blade. The reason why it's swept back if you're processing fibers, right? Fibers will get caught on the impeller blade and eventually work themselves off the back end. So swept back is very useful for fiber material. Swept back pitch blades are possible. And we go to all sorts of other variations out there. Again, anchor impeller. This is a pretty desperate impeller. It's used everywhere. And by desperate, it consists of actually two types of impellers. I mean, two types of flow. At the bottom here, you have a fairly well-mixed area because you have substantial radial flow impeller at the tank bottom. So there's very good flow along here. And the top portion of this tank is not mixed at all, hardly. Okay, so you have a well-mixed region for the anchor, and then you have a poorly mixed region up at the top. There's very little flow that goes up and around, right? So what happens in the top region of the tank is fluid at the wall. The blade passes the fluid at the wall. Fluid lifts off the wall and goes back to the wall as the blade goes on. So what you do is you make a helix out of this. You make just a simple change out, make it so that these things have a helix associated with this helix here. Okay, so you take it and twist it, and then you get a helix. That would be a great anchor. Excuse me, it would be, you have the benefit of the anchor with up-down flow due to the blades being twisted. So up here we have single ribbon. Double ribbon works a lot better, right? Single ribbon's fine, it's sort of like okay. But again, I would have the tendency to get rid of these support arms and come and mount it on an anchor, such as this. And then I have a much more ideal mixer, as we will talk about a little later. We have our old buddy screw impeller in a draft tube. This is not bad, but again, you got to worry about, I don't know if you want to worry about a draft tube or not. The purpose of a draft tube is not necessarily understood very well. What a draft tube does, however, is create uniformity. Without the draft tube, you got more non-uniform flow. With the draft tube, you have more uniformity. Okay. Some of these other impellers, you take this one here. You have a single ribbon, and then you have a screw mounted on the inside. So the overall pumping, you may be pumping with the ribbon and then pumping down with the screw. The problem with the screw impeller being like this is you have a situation where it may not work the way you think it does. Okay, the ribbon is a high pumper. It pumps a lot. It may have a low pumping number, but the diameter of these blades is almost to the wall. So you're creating a significant pumping action with the ribbon. Now then it comes up at the top and it runs into the screw. Now the screw impeller could actually slow down the pumping or block the pumping of the helix. So you have two ways that this thing can happen. The ribbon may help you in pumping, or it may block the flow of pumping with the helix. So you got situations where screw's helpful, screw is not helpful. So even though it looks like a fantastic mixer, and I'm sure there's some places out there that use this, it's not exactly clear when the ribbon benefits or when the ribbon doesn't benefit. Then we have our famous impeller that's sort of, I guess, a homemade concept, is that you have the liquid, okay, and then you have submerged solids, and you have the impeller buried into the submerged solids, right? So as you start up this impeller, if it was a flat blade impeller, the blades would break off, right? And it causes all kinds of problems and maintenance and whatnot. Kaolin clay industry typically uses a spring, a truck spring, and it's mounted on a shaft, and that becomes the impeller. Okay. So as you start a truck spring blade up, the spring will deform but won't break. Okay. And so you eventually, with a truck spring here, dig yourself out of submerged solids. So again, you're looking for performance out of these mixers. You're not looking for geometric similarity. You can certainly improve things over the standard geometries that are sold off the shelf. Okay. And as I said earlier, liquid level does change. You always need an impeller on the tank bottom, thick clear impeller, because liquid level is going to change on you. Also, you need to watch out for what happens as the liquid level passes through the impeller as it drops or increases. There will be a splashing zone, right, which may or may not be a good idea, may cause problems. So you have a whole host of geometries here. You need, if you go back to this one, right, swept back, proper mounting, and then you have a whole bunch of these. The old saying is, when in doubt, use a pitch blade turbine. The reason why you have a pitch blade turbine is these blades can be unbolted and fit through a manhole and then bolted back up. The hydrofoil can also have that design, and of course we have the famous marine impeller. All three of these are great designs. Some will have advantages over the others depending upon the application. Okay. Going back to those, and then further, we have, might be referred to as high soliditude impeller for gas dispersion in viscous liquids. Now, you may or may not have a box fan at your house, but a high soliditude impeller is the impeller of choice for a box fan, right? In a house, 3 by 3, 3 foot by 3 foot, and an impeller inside. It's called high soliditude because you can't see through it. You always run in. Anyway, high soliditude impeller for gas dispersion. I've had 2 stories about this. My friend at a very large pharmaceutical company said these things are fantastic for what they were using it for. Large area blades are very important. Blade area can be quite significantly important variable if you look at the mixing literature. Okay. And he said it really worked well. Another chap I ran into said that this was absolutely terrible at gas dispersion. Right? So he put it in thinking it would be wonderful, and a couple of days later, he discovered it's not doing so well, so they took it out. The follow retreat blade impeller looks like a chicken foot, and very important. It's often 0.7 In other words, tank diameter is T. The impeller diameter on a Fodler design is 0.7 T. In other words, it's a large diameter impeller, and that's what lets it get away with a whole bunch of stuff. It's a large diameter impeller. It's often basically used in glass-lined tanks. Glass-lined tanks are used primarily to keep the reactor wall or the wall of the tank from participating in the process. Glass is fairly inert, so you also glass-line the impeller as well. Now, it's 0.7 the diameter of the tank, and when it's put close to the bottom impeller, which is obviously a good geometry. And what it does, it revs the fluid up along the wall. Okay, and there's a big center vortex drawn. And that's the way where you would add your powders or your other material right into the center of the vortex, goes right to the impeller and gets dispersed. However, with the retreat blade Fodler impeller, as you increase liquid level, the nature of the flow, it's still rotating around, but the surface vortex is not nearly pronounced. And as you get to fill the tank all the way up to the top, the center vortex is no longer there, no longer prominent. So the problem with the retreat blade impeller here, Fodler, and other designs, of course, that compete with Fodler, you have the general circulation in the tank varies as a function of fill height, right? Low volume or low up, you have a center vortex very large. When flow goes around and around in circles, when it's filled completely to the top, that's no longer curves that much. So the problem with scale up of this thing is depending upon the volume, the flow field is dependent upon the volume of this. Okay, then you have the famous back and forth impellers. I don't know if you know about these, but you take somebody stirring coffee, putting sugar in coffee, and they'll use a spoon, and basically that's an example of a back and forth impeller. Now, what's interesting about these are highly efficient impellers. I mean, spoon's highly efficient in dissolving sugar. Right. If you add sugar to coffee and not stir, the sugar will go to the tank bottom, not dissolve. Right. But if I take my coffee with sugar and stir it with a spoon, it will dissolve fairly quickly. So again, back and forth. What's of course interesting is when you run across people that after the sugar is dissolved, they continue to stir. Okay, back and forth, back and forth. They love the feel-good feeling of stirring their coffee. Of course, the sugar's dissolved a long time ago. Then we have impellers in planetary motion. Now, as we get to later, you do not want to use a turbulent mixer in a laminar application. You do not want to use a turbulent mixer in a laminar application. Unless, of course, the turbulent mixer is in planetary motion and covers the entire tank, right? So there's a lot of rationale in here. So impellers in planetary motion covers up a lot of sins and are very useful as well. Usually the direction of rotation may not matter, but they do matter, obviously, if you have axial flow impellers or also the Smith impeller. Direction of rotation may matter. Generally speaking, it doesn't. But that doesn't mean that it can't happen. Anyway, moving right along. Standard geometry in turbulent flow is often called the standard mistake, right? I remember reading this when I was a young child, young 18, 20-year-old child in fluids course, McCabe and Smith, reading about the standard geometry. Well, you can consider that a standard mistake. First off, geometry is one of the fundamental variables in design. Design consists of two major items: getting the right operating conditions and getting the right geometry. So geometry is key, and if you believe in geometric similarity, what you've done is destroyed one major design opportunity or design variable. If you get it right, everything goes right. If Get it wrong, everything becomes difficult. So, geometry depends upon the Reynolds number. We have the Reynolds number, and I suppose you all have calculated your Reynolds numbers. Okay, below 100, you may have laminar mixing, which means you should use a laminar geometry, which means a helical ribbon, the bottom scraper. Above 5,000, you're in turbulent regime. You want to use a turbulent mixer with an impeller on the tank bottom. Okay. Between the two, however, you have the fantastic transition regime. Okay. And the transition regime is often referred to as the problem regime. We can process in laminar flow, not too much problems. We can process in turbulent flow without too much problem. The transition regime, however, may be difficult for you. It's often considered that the transition regime may be considered the failure regime if you're not quick on your feet, so to speak. And just for kicks, we do a quick Reynolds number calculation. I have 1 meter diameter impeller going around 1 revolution a second, 60 RPM, and the Reynolds number is a million, so 10 to the 6th. Then I switch it out. I have pudding. I forgot to mention viscosity up here. Kinematic viscosity of water is 1.4 times 10 to the minus fifth, meters squared per second, I think, in which case you can do the calculations. Pudding, on the other hand, may be 1,000 times greater viscosity than water. So again, you have 1 meter impeller rotating at 60 RPMs per minute, right? You have a Reynolds number of 1,000. So you go from 1 million, which is probably the Reynolds number of milk. And as you cook your pudding, the pudding particles swell up and significantly increase the viscosity. So you have a big difference between flow between milk and pudding. And an experiment I want you to do to let you understand this further. So I want you to cook some non-instant pudding on the stove. And note the transition point where it goes from turbulent flow, which is the milk, to laminar flow, which is the pudding particles thickening. And the big point is you don't want to burn your pudding, right? Big. If you go in a laminar flow, you have a tendency not to stir as much. If you're using a spoon, which is a very poor geometry, you'll notice that the contact point between the spoon and the bottom of your pan is a single point. However, if I come along and get smart and get a spatula, which has a long flat edge to it at the end, I go along and I scrape my pudding. I'm not touching it at a single point. I'm touching it all along the length of that flat edge of the spatula. So there's an example of cooking with an improper geometry leading to your pudding being burnt, i.e. the spoon, versus using a spatula, a more effective device in scraping the surface, and I don't burn my pudding. So, example of a change in geometry, which has a significant impact upon your pudding. Now, that's extremely important to have unburnt pudding. Anyway, again, we reiterate, don't use a turbulent mixer in a laminar application. You can see a number of companies using turbulent mixers in a laminar application. Need I say which ones of you are out there? You can confess up if you wish. But, it's like everywhere. Okay. It's all right, gives me something to talk about. Lots of different mixing methods out there. I don't know if you realize it. Most of the mixing companies want you to focus on their mechanical agitators. But you forget there's jet mixing, there's natural convection mixing, there's shaking and tumbling and bubbling and boiling, all kinds of these things mix, right? in, say, processing, making steel, and they have this big ladle full of molten metal. You can't very well put an impeller in there because the molten metal would simply melt the impeller. So what you'll do is you'll go in and you sparge with a lance, probably a ceramic lance of some sort. Go in and sparge with oxygen, maybe, if you want to have a real good time, or an inert gas to cause the mixing to go along. So mechanical agitators mix by putting in a certain number of revolutions. I call this the number of revolutions to mix. So this is the NRM, number of revolutions to mix. Processing depends, lots of processes depend upon the number of revolutions to mix. Okay, and these typically go from 15 to 3,000. It's typically the range of effective equipment. Maybe 3,000 revolutions may be a bit high, but maybe 1,000 revolutions. So you have shaking, tumbling are very similar to mechanical mixers. It's the number of tumbles or the number of shakes that matter. That's what physically is affecting your process. So anyway, getting back to jet mixing is up here. Mixing by entrainment along the sides of the jet, very important. A freely expanding jet is what you want, right? So I have another assignment for you. I want you to go home, get a glass, fill it up at the spigot with, turn on the water, let it flow into the glass. Take a look at the glass and see how well mixed it is. It's extremely well mixed by the jet coming out of the faucet. So as an example of really great mixing. And boiling and bubbling are similar to jet mixing. Bubbling and boiling, you have another phase there, steam or bubbles, nitrogen or whatever. And as the bubble rises, so it pulls behind it a column of liquid. So you have sort of very similar jet mixing behavior. So to give you an idea of jet mixing, here's a picture, the structure. Flow enters the jet. This jet's freely expanding, okay? And flow enters the jet perpendicular to the jet. That's just the way it works, right? And participates in the flow field. So you got some sort of velocity profile here. You got a mixing zone here between the outer region of the mixer, okay, and the inner region. The inner region might be very laminar-like. Here you got freely expanding jet. Most of the time you don't think. You got this big storage tank and you go in, yeah, we have jet mixing, and you shoot the jet along the tank bottom. That's primarily to take the solids off the tank bottom. And perhaps you have a device that swirls the jet in different directions along the tank bottom, so you clean the tank bottom. However, if you're looking for turnover, right, you have another set of jets such that they're, suppose you had some sort of stratification going on in this tank, and you want to have some sort of top-bottom turnover, right, in which case you have the jet freely expanding. That way you have a large surface area available to mixing. And if I was trying to have a large turnover, right, I want to have the largest surface area here. So I want this jet to be freely expanding. Okay. This is for a very large surface area, very large tanks, maybe 40 feet in diameter, or 40, large. Okay, over here I have an interesting situation where I claim all mixers are pretty much the same, right? All depend upon how much power you put in. But here I have the mass transfer coefficient maybe hanging in this region for agitated tanks. At higher power levels, it may be here. But the correlation collapses along the side. I don't know if that's significantly important. Here we have the solder mean diameter versus the Weber number. But again, down here, getting back to this, I said you have a jet at the bottom sweeping, right? So that's one geometry for off bottom suspension. And you make sure the jet moves back and forth so it covers the entire tank bottom. Or I change the geometry and make the orientation so that it has an angle that allows a freely expanding jet to form. So again, a change in geometry, change in objectives lead to a change in geometry. And it's basically dictated by common sense. A little bit of thought. Lots of processes in different geometries are similar to each other. It's useful. You have the same physics occurring, but different equipment. Again, if I go back to this, same physics occurring, but different equipment, different energy levels. So I have different geometries. I have different power levels, but they all line up. It's interesting how that happens. Optimum points. Now, there's always optimum points. And this may actually be a justification of research in mixing. Mixing is often taken as a sort of guarantee. It's not. Okay. Mixing does not have to occur. Turbulent mixing is often so easy that you don't pay necessarily any attention to it. So I have an old process. 90% of the time is spent elsewhere. 10% of the time is spent mixing. So if I go to a new process where I got some mixing hotshot come in, all right, you have a design that's new. The 40% didn't, the 90% didn't change much, but the new design dropped your mixing time down from 10% of the total down to 3%. Add up the numbers, and you find that I have a 7% increase in production. Now, mainly that doesn't bother much people in some cases. In other cases, that might be significant to you. So operations at optimum points are economically significant. These are not available from the general correlations, optimum points. So it gives you an example. So let's go here. This is, you got to close your eyes and your ears now. This is the reactor that the government uses to make plutonium. Okay, close your eyes. Anyway, just kidding. This is a mixing in a slab tank. And I was using up-down mixers. So this thing goes up and down. I was using 1, 2, varying the clearances. I even had a slant mixer in there. All this is summarized with Chris Ramsey, AICHE, in 1989. Anyway, we have the homogenization number. Now, that's a fancy word for a number of strokes. Right, this is up-down mixer. I'm not looking for RPM. I'm looking for strokes. So I have the mixing capabilities of these things. You put in a die. You count how many revolutions the die takes before it becomes uniform. So we took videos, and we noticed that there was a particular width to tank thickness. The tank thickness was pretty much fixed at 4 inches, but the width, right, it was 0.75. There seems to be a minimum here. So the number of strokes to mix was roughly around 20 here. And way up here, it's 60. So literally, by the way, the whole process mixes, right? But now I can mix it 60 strokes or 65 strokes, and I'd reduce it down to 20 strokes if I use the proper or a better geometry. This worked. Right? This gets the job done. This one does it with higher efficiency. So what you want to do in industry is avoid procedural mixing. Now, this is everywhere, right? Everywhere. And typically, you see it in procedures, add and stir for 30 minutes. As we'll see later, mixing's over in maybe 1 or 2 minutes. So what's the other 28 minutes for, basically? What's the rest of the time for? Is it a feel-good time? Does it help you? No, it doesn't help you with it, doggone. So going forward, you could probably say that lots and lots of industries are over-mixing simply because they have a feel-good time about themselves, right? Anyway, count. You need to pay attention to count. Count determines mixing. Example would be a static mixer. Typically, you need 3 static mixers to mix in a turbulent zone. And videos will show you that. Okay. If I go to laminar zone, laminar flow in a pipe, I don't have good mixing with laminar flow. It may take 12 static mixers to mix for laminar flow. And of course, we have the number of revolutions to mix for mechanical mixers. And we have drums, rotating drums that tumble. It's the number of tumbles that is important, not the time, right? Time is really a fairly odd thing, right? To say a process is over with in a certain amount of time is probably a gigantic misstatement. Okay, let's give you an example. I have some clothes I want to dry, and I want to put it in a dryer to dry, right? So I put the clothes in the dryer, but I don't turn on the tumbler action, but I pass air through it. The hot air goes through, and after 40 minutes of drying time, the clothes are not dry at all. So then I put the tumbling action there and repeat. So over a 40-minute period with tumbling action in there, the moisture was exposed to hot air and evaporated off, so my clothes are dry. All right. So the time spent inside of a process doesn't mean anything if there hasn't been anything that has happened, right? If it just sits there, all right, it hasn't gained anything. I have students that will come in and sit down in my class, not do anything except go elsewhere. So they're in my class for 50 minutes and they didn't learn a doggone thing. Terrible person that I am. Anyway, I don't force the issue. Let's go back to our dryer now. Okay, we turn on the dryer action, right? So we have hot air and tumbling going on. Okay, and after 40 minutes, I open the dryer. I expect the sheets to be dry, clothes to be dry. Unfortunately, the sheets have balled up into a ball. And essentially, inside that ball, the sheets are still moist and not dried. So even though I have tumbling action, I have a bad flow regime. The clothes are all caught up in a big ball. So then I have to break apart the ball, put the clothes back in the dryer, turn on the dryer, and process some more. Flow regimes are critical. You need to pay attention to flow regimes. Okay. Flow regime changes can lead to process failure or unsafe operating conditions, and you wind up dead, right? Anyway. So anything that rotates, rotator, dryer, extruder, agitated tank, powder mixing, right? Agglomeration processes, crushing and grinding operations, all determined by the number of revolutions. Right? Grinding to a certain particle size, you have to put in 1,200 revolutions. Has nothing to do with time. Right? Time can be quite misleading. But you need to pay attention to your process and characterize your process, not according to time, but according to flow regime and the number of tumbles and what the flow regime looks like. The other thing in procedures, you don't want to cause the problem to begin with. Right? Adding powder or liquid will form lumps. The lumps are a problem, so your procedure causes problems. Yeah, that's the way they did it in the lab. Hey, you do not want to do that. What they did in the lab is one thing. What you want to do in the plant is maybe quite different. Lumps take a long time to dissolve. In the lab, they just reach in there and crunch those lumps. But if you have a 10,000-gallon large tank that has a manhole to it, reaching in and breaking lumps apart with a big spatula is not going to pay off. Example is adding liquid to a wall. If you add liquid to a wall, it'll stay at the wall for an awful long time. So if you make an additional liquid expecting it to be reacted and you add it at the wall, you can very easily think that it stays at the wall for quite some time, and you don't know how long it's going to stay at the wall. Right? So don't cause problems to begin with. You want to be smarter. Other than that, if we go along here, this is some, I took a long time getting the computer graphics package to give me these plots. And these plots are made to look like hand-drawn figures. Just kidding, just kidding. We had two pharmaceutical companies in Jersey, right? You had one company, this is non-mixed situation, and this is mixed situation. Okay, so one company took data points every 5 minutes or so, whatever, and validated on a mixed time of maybe half an hour, or properly stated, 180 revolutions. Another company comes along and takes the data points here, 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 and here, and validates on 18-hour mixed time. So, see, powders have a habit of mix, demix, mix, demix. Okay. You may think that they can't demix, but they will demix. Different densities, different shapes, different velocities, different sizes. There's a whole bunch of reasons why particles demix. You take a look at the standard cereal box at home. You got all the fines at the bottom of the cereal box. You also have a whole bunch of sugar down there, so young children always spot out where the sugar's at and want to always have the fines at the bottom of the cereal box. Such is the way of young children. But I find this amusing that the company didn't understand mixing. One company went out of business. 18-hour validation is a pain in the neck, especially when you did it wrong. Over here, I took this from Jim Olshoe, thought it was interesting at the time, so I mimicked it. Over here, we have performance index, and down here, we have power per volume, right? So up here, we have poor performance going to good performances. Power per volume goes up. This is tank-controlled processes. Coalescence is a tank-controlled process. Then you have mixing control processes, right? Dispersion would be a mixing control process. And you have excellent performance as you go up with increased power per volume. Over here, the impeller geometry matters. Over here, the impeller geometry doesn't matter. Again, you have a change in the nature of design. All right, kind of interesting. Impeller control processes, you got to figure out what those are. And tank control process, you got to figure out what those are. Anyway, the killer. The killer is, this is given to me by a friend of my acquaintance inside one of the major chemical companies. Is typically you have the tank bottom, then you have the exit nozzle, and after some distance here, you have a control valve. And what happens is this open space in here is a void that lets solids accumulate. And if we know about solids, the first thing you know that solids do is probably agglomerate, which means you should review my agglomeration course. So the way you get rid of this problem is put a flush mounted valve here so there's no volume here that material can be caught into. This is a very safe, this is a very unsafe geometry. And it has a nickname, the killer, right? It's everywhere in industry. You should be aware of the fact that potential plugging here may kill you. Sorry. It's the way it is. Case in point, example, this one company had this design for a premix tank to a polymerizer. And basically, this premix, they mixed the initiator with a monomer in here. So they started up a batch right before Christmas. They put in the monomer, and then they added the initiator. And they didn't have enough initiator, so they decided to wait until after Christmas. So during Christmas time, 2-week period or so, or a week period, there was a plug that formed down here with what little initiator there was accumulated here, and the monomer, so it formed a big plastic plug sitting here. So back from Christmas, they added more initiator, and so they finished off the recipe, and so now they have an initiator and a monomer sitting in there, and it's well mixed. So then they go to push it to the reactor, and got a bloody plug sitting there. And so the previous name to this was premix tank. Now the name of it has been officially changed or unofficially changed. It's no longer a premix tank. It's a bomb. Initiator, monomer, and the safety conditions was not up to snuff to be able to handle what's likely to be a runaway reaction. So that was 10:30 in the morning. They found out that they couldn't push this stuff. They didn't know what to do. So now, because the plug formed, they're going down a road that the procedures they have no procedures for handling this situation. Of course, you should have realized that this group of operators don't follow procedures anyway, because when they added the initiator and the monomer, and they didn't have enough initiator to complete the process, the procedure said to drum it off, okay? Put it in drums. If you couldn't complete a complete cycle all the way to the end to a push, you were to take whatever material was in here and put it into drums. Okay. Now, people involved with this process, they're thinking people. Okay. And they said, well, what's the difference between having it sit here in this premix tank or drumming it off into separate drums? Why not just leave it in the premix tank? Save us some problems. So they didn't drum this off. The procedure told them to drum it off, but they didn't follow procedure, and they don't know why it would be a hazard. But it was. And I suspect that nobody anticipated a plug being formed. Anyway, this was at 10:30 in the morning after Christmas break. So they come in, and now they have a bomb sitting here. So 11:30 that night, the maintenance shift changed, right? The maintenance people went up, started banging on this. Well, one maintenance chap started banging on this, thinking it was just a premix tank, but the name now has been changed to bomb. So he's banging on a bomb. And the bomb goes off, and he was not well treated by the process. Let's put it like this. 70% of his body was covered with molten plastic, and he died 6 months later. So, I've been in the chemical industry, or around chemical industry since the 1960, and I'm afraid to say that nature has a habit of reaching out and killing you. It's unfortunate. I don't like to say that, but it is indeed true. Okay, let's move along. Some of these other graphs. So you need to, procedures ought to be written such that you have the procedure. Okay, the next column over, procedures ought to be 4 columns long. This next column over is what will happen scenario-wise, accident-wise, if the procedure is not followed. Okay. And then the third column over would be some sort of information about any accidents that are similar to your process, such that this is the accident that can happen if the procedure is not followed. And the fourth would be some sort of statement about documentation. Procedures are often so unspecified that it gives too much freedom. Okay, you want freedom, but you don't want too much freedom. So there's a balance struck there. Anyway, moving along. There's another picture that I've taken from Jim Olshoe. I really like Jim. He was a nice guy. Going from small scale to large scale, you're increasing volume effects. So you have significant increases in volume, which is, I suspect, not very well appreciated. Now then, I have a problem in the plant and I want to scale down. As I scale down, I have more surface effects. So increasing in size, I have volume effects appearing. Decreasing in size, I have more surface effects happening. Case in point, I have foaming in this small reactor, right? Large reactor may not have any foaming whatsoever. Foaming being a surface process of sorts. So I have processes which change with size. That's another thing you should recognize. Processing should change with size, and if you're using a laboratory procedure in larger sizes, you should reanalyze laboratory procedures because the large-scale process is quite different than the small-scale process. Large-scale processes are sluggish, takes a long time, right? All kinds of things. Small-scale process, quick and done. An example would be if I had a water line in the bathroom, a water line faucet in the bathroom. I can turn that on and off fairly quickly. If I have a 3 or 4 foot diameter pipeline, 15 miles long, and it's moving at, say, 10 feet a second, there's significant differences between that pipeline and the pipeline in my kitchen sink or my bathroom sink. So you got to pay attention to size, even though they're, quote, geometrically similar, they're significantly different, right? Anyway, I like this one over here. This is the n theta value, number of revolutions to mix, as a function of impeller Reynolds number. And what's interesting is the black line is optimistic, right? The red line is probably what happens as soon as you go into the transition regime. You already have poor mixing. And you go in a laminar regime, this thing goes vertical. You may never mix stuff in the laminar regime. Case in point, this is using a turbulent mixer in a laminar application. An example would be making whipped cream at Thanksgiving time or at holidays, you're making whipped cream. After the whipped cream sets up and becomes firm, you use planetary action to do that. However, if I take the impeller and put it on one side of the whipped cream bowl and add sugar on the other side of the whipped cream bowl, the two won't mix. So that means the n theta value goes to infinity. So you go into planetary action, again, going to a full tank impeller. It's kind of neat. I ran across the process. It was quite strange. It was in Vermont. Okay, sorry, guys. I won't mention your name, but appreciate the opportunity. Anyway, it was difference between summer and winter effects here. In the wintertime, they heated the building in Vermont, right? The building in Vermont was heated. That means the storage room was warm, right? So the storage room was warm. That means the viscosity of the material was low. So they were over here in this region. Most of the processing they were trying to accomplish was high Reynolds number turbulent flow. Now, that's the winter time. Everything's fine. Now, summertime comes along, and in Vermont, it's still reasonably nice weather. However, oftentimes the air conditioner is used. And in this case, they air conditioned the inside of the building. I would make a bad comment, but I shouldn't. I mean, I would probably want to say something like, Yankees really don't understand air conditioning. But I shouldn't say that. That's terrible. I apologize for that. Anyway, so they air conditioned the entire building. That lowered the viscosity on their material. Ever so slightly, 10 degrees. Instead of being 80, it was 70 or 65. So then, therefore, the viscosity dropped. The viscosity went through the roof, and as a result, they couldn't mix the material in the summertime. They could mix the material in the wintertime. So that's an interesting difference in storage environment causing processing problems. This is N theta, and we have a D over T effect in there. It's great. You have the Reynolds number, and you see anything above 10 to the third, everything's kosher, or everything is great, and below 100, it's going through a roof. Now then, I claimed further on back that the helical ribbon was a universal mixer. Here's a helical ribbon. This is brought to you by some Czechoslovakians, and it was back in the communist time. Okay. So I don't know if that matters to you or not, but you should. Their results look quite reasonable, actually. Over here, this is Reynolds number, and this is power number. And on this side is the number of revolutions to mix. So you have the power number going up, okay, which you would anticipate, right? More power draw because of the high viscosity. High viscosity causes low Reynolds number. Power is proportional to viscosity. Okay, in laminar mixing or creeping flow mixing, power number has no density in it, right? You have the laminar power number and you have a turbulent power number, and you know to understand both of those. And for that, you need to watch my video on paste and high viscosity processing. Anyway, in the laminar regime, it takes about 60 revolutions to mix. In the turbulent regime over here, it takes 40 revolutions to mix. So it's not uncommon for processes that start out turbulent to wind up in laminar. And that's where the helical ribbon does an excellent job. It's a universal mixer. It handles the turbulent stuff. It handles the laminar stuff or creeping flow stuff. Anyway, what it doesn't handle very well, or not as well, is in the transition regime, okay? In the laminar regime, viscosity is everything, density is nothing. In the turbulent regime, density is everything, viscosity is really nothing. So you have the transition bump that occurs here, where the two regions meet, viscous control, density control, and the two meet, and that's called the transition bump. So that takes about 300 revolutions to mix. So when you're starting out turbulent, passing through transition, going to laminar, example of that would be cooking pudding on the stove. You start out turbulent, go through transition, you burn your pudding in this region. So this has an impact on your processing. Or shall I say, if you're going to change from low viscosity to high viscosity, you got to watch out for the transition regime. Effective mixing is determined by the number of revolutions to mix. Good mixing doesn't require high power input. This is very true. Can be attained by low power input. There are many, many useful designs. Many designs don't mix. You're always looking for good axial pumping. Anchors are not good. Helichrym is recommended. Okay, just some sort of comments there. Now, this is what happens in the laminar flow regime. Excuse me, when you use a turbulent mixer in a laminar application. So I have a pitch plate or I have a Rushton, disc style turbine. Rushton was a very famous mixing guy back at Purdue. Also, I think he was research director at Lightning Corporation. You have a small diameter to tank diameter, small D over T ratio. And so you form a well-mixed cavern, right? And the outside is stagnant region. And you can think of this as what happens when you're making whipped cream. Whipped cream, you'll have a well-mixed region around the impeller, and further on out, due to yield point or whatever, you have no motion. Now then, if I go to a full tank impeller, or I go to a higher diameter, tank diameter, impeller diameter, tank diameter, I have the cavern grow larger. The impeller grows in size and the cavern grows larger. So eventually, if I go to full tank impeller, I have the entire batch well mixed. Lots of polymer companies have used turbulent mixers in a laminar application. And typically what you wind up having is two different reactors here. You have a reactor that's well mixed, and you have another part of the reactor undermixed. So you have one size of particles being produced here and another size of particles producing there. So you have a broad distribution of particle sizes and or emulsions, polymerization happening if you're doing that. You're going to a full tank impeller, then that tendency, you'll get a much tighter distribution. It's really funny. I go in, talk to a polymer company or a paint company or whatever company. I won't comment about the chap that I met up in Minnesota. He's a collection of stupidity. Anyway, they're pretty funny. It's pretty funny listening to business people or these young managers judging old crusty people like me. It's pretty funny. He was quite an amusing little fellow. Anyway, it's not uncommon for me to walk into a polymer company or emulsion company, paint company, and they tell me they have a broad distribution in their particle size or their emulsion, whatever size. And I then tell them what impeller they have, and they get highly threatened by that. They have a bad geometry in their reactor, and they continue to live with it. And as a result, they're going to always have a broad distribution. Anyway, that was quite amusing. Some people at paint companies are really nice people. Some are right down dumb. Anyway, sorry. Proceeding right along, D over T ratio. Okay, very important dimensionless group. D over T ratio is your friend. Obviously, the higher the D over T ratio, the more important the impeller is, and the performance is improved. So you have this D over T ratio occurring in various processes. Should be recognized, should be used to advantage. The impeller, in a sense, is the area generator, and the tank storage for the area, but as it's being stored, it will destroy the area. Again, this idea of a tank process versus an impeller process. Can be used as a diagnostic tool, very important, D over T ratio. Temperature measurements can be used as a diagnostic tool as well, an idea. In other words, if you have a small impeller, it's not going to be felt in the bulk of the tank. In other words, if you have a small impeller, the type of impeller doesn't really matter. Okay, you can expect D over T ratios in blending, selectivity, yield for fast reactions, flow at the wall heat transfer. If I have suspension problems, the D over T ratio matters. If I have a buoyancy, solid submersion problem, recirculation dependent processes, driving force for mass transfer. D over T ratio is poorly understood and not studied. There is an optimum impeller to tank diameter ratio for most processes and process objectives. Anyway, about the technical literature. Now, there's a whole slew of mixing articles out there. I think I read, 2,000 articles to write my first book. Read an article a day and summarized it one page at a time. Anyway, after reading that many articles, you get a fundamental understanding for the technical literature. And technical literature is extremely valuable, extremely valuable. I was up there visiting a specialty chemical company in Philadelphia, and this chap, very educated chap, good engineer, he was describing what he was going to be doing for the next 6 months. And I reached in and pulled out the article that I had because I was reading an article a day, right? And I explained, here's your results. So he had the idea of what he was going to do. It's already been done. Technical literature was already published, so I handed him the information. I thought that was kind of cute. I appreciate the chap. But never underestimate the technical literature. I like to use the technical literature to solve mixing problems. So you need to keep current. Of course, upper management may not appreciate you wasting all your time educating yourself. Let's go on to power and fluid motion. Power is energy per time, added to the process in many different ways. Mixing device, an impeller adds power. However, the process itself may add power. If you have a boiling process, it's well mixed. If you have an impeller in there, it's well mixed. Power is also dissipated by fluid motion. When you have a cup of coffee, I want you to stir it. And, well, better yet, I want you to take a cup of coffee, put some cream in it, and see how long it takes to mix without stirring. It will be an awful long time, depending upon how your jet mixing occurred when you added the cream. If there was substantial jet mixing when you added the cream, then you're probably mixed. If it's slow adding the cream and you add along the wall, so there isn't any flop out, so to speak, then it'll take a longer time for it to mix. But anyway, you stir the cup of coffee, see how many rotations it takes to mix the cream into the coffee, and watch it slow down. It slows down not by acts of God, but by fluid friction. Right. So power determines other process quantities accomplishes the process objectives. Power makes things happen. Power delivered to the process should be measured, if you can, with a power meter. Rotating equipment, you can run empty, run full. And the difference may be give you some indication of the power being added to the process. You should also calculate power. And you should analyze the different power sources in your process. Identify the important power sources. You have jet mixers, you can have mechanical mixing, you can have I already said jet mixing. So there's various ways, boiling operations, right? Gas sparging operations. By performing a power analysis, which is never done, right? Probably never even heard of it. But anyway, one can judge the importance of different power sources, right? And here we go, right? Power source of mechanical agitation, jet, gas sparging, boiling, falling, liquid film, shaking, natural convection. And all these can be important, except for falling liquid film. That's pretty desperate. Anyway, you do the calculation of power input. You have the impeller. This is power input from impeller at different conditions. You can see it puts in 0 or practically 0 power to a whole bunch. Now you get fancy and you start doing power per volume, which is useful. And you also want to think about it as horsepower per 1,000 gallon, perhaps, if you want to go more industrial. And then you have jet mixing. Power input can go from very little to very much, a lot. Gas sparging as well. You can go from very little to a lot. Boiling liquid. Again, boiling liquid is well mixed. Falling drop into a liquid, very small amount. Liquid sprays can be quite a bit. Falling liquid along the wall might be very small. Anyway, so you can put in a whole bunch of power or put in a whole bunch of no power. So should do a power analysis. For those of you who are engineers, a power analysis is typically done for pipelines, right? So pressure drop through fittings, pressure drop through a heat exchanger. You're doing a power analysis because I take that pressure drop times volumetric flow rate, and that gives me power. So when I do pressure drop in pipes, calculating pressure drop in pipes, I'm doing a power analysis of that piping system. By analogy, I carry that over into an agitated tank or into a process, and I measure power by the various power input measurements. Quickly, you'll see there's no dominant power input mechanism. Any mechanism can put in power. Important that power is utilized. Lots of power is wasted. Many processes depend upon heating, interfacial area, mass transfer. Lots of processes do not dependent upon power. Mixing, for example, is the number of revolutions. You can put that revolutions in very quickly at high power or very low power, nonetheless mixed. Solid suspension tends to be independent of power. So some processes depend upon power, some processes don't. Interfacial area will be always power dependent, right? Because you're looking for mass transfer is interfacial area. Here's a question I got from one of the participants in my short courses. The chap asked me he was making an emulsion, and he asked me what could I do to improve dispersion capabilities of the impeller. He was doing liquid stuff. He asked me what he should do to the impeller. Well, the question is, where's the emulsion being made? Is it being made around the impeller? Is it being made in this pump? Is it being made both places? Mixed, or is it being made by this feed jet as it comes through? There could potentially be feeding an emulsion to a high pressure drop through a nozzle. You could substantially make drops here. So you have 3 places where drops being made. Power analysis might help you understand which might be the dominant power mechanism. Basically, you're looking for trailing vortices and high shear zones is typically vortices or high-speed jets. Anyway, this is an interesting slide, very famous slide from way back when. Remember using turbulent mixers in a laminar application. So quickly we say that this information here should be noted that you shouldn't be operating using a turbulent mixer in a laminar application because you're not going to do very well. Okay, so this is somewhat, anyway, we'll let you form your own opinion about that. Then the curves go flat. So I suggest that we have different impellers. I suggest that the whole graph could be reduced to a simple table. Power numbers being peeled off here as a function of geometry. So it's very interesting. Very pretty graph. Very gives you the impression that they know what they're doing. Fluid motion, how materials moved about, causes a lot of contacting between materials. causes the process objectives to be accomplished. So flow field should match the process. You're looking for three-dimensional motion and mixing. Good bottom sweeps for solid suspension, right? Solid suspension is a bottom process. You don't want the solids down there mixing with each other because they could potentially react together and form strong bonds and give you a new tank bottom. That's not a good idea. Impeller vortex systems for dispersion processes. That's great. High shear region. Two-dimensional solid body rotation for crystal growth. Details. More of the blades, the better. Now, I studied that. More blades, the better dispersion. The exponent on blade number is 0.4. It's not. If you had twice as many blades, you do not get twice as much performance. If I make twice the impeller blades, I take 2 to the 0.4 power. That's what I would anticipate the improvement to be. I did that for moldable impeller blades for a gas dispersion process. Anyway, we have this lovely picture by Smith and Van Riet. They have their lovely vortices being formed behind the impeller blade. The front of the blade does actually very little. It's the back of the blade with these vortices that does the fantastic processing. And I've added the high-speed jet in between these two vortices as an improvement. So if I go along, these vortices are in flat blade impellers with a disc there, and even for a pitch blade turbine, and they also are available with the hydrofoils and propellers as well. And you got some really sensational videos on YouTube about vortices forming off of boat propellers. Anyway, this is a gift. I appreciate the person who gave it to me. This is coming from a pharmaceutical company. I won't tell you the name, but it's in North Chicago. Anyway, two-dimensional flow. This is given during the class. The person just stated it out that they had run a cone bottom study and they were watching the volumes of liquid, and it was a crystallization process. So they were adding crystals to what amounted to being a solid body rotation phenomenon. There were no baffles. It was not turbulent, but it wasn't quite laminar either. So it's probably in the transition regime. Anyway, it went around and around. No real breakage going on. I mean, the stream was feeding back upon itself. Turbulence, this would not happen. So you had solid body rotation. The crystals are fantastic. The crystal growth was fantastic. They were able to filter it easily. So then they went full volume. They included the baffles. Now the geometry switched to turbulent. So then they had the feed. Now the solid body rotation, you had the feed zone coming back upon themselves. But in the turbulent, you got to have mess every which way. Particle crystal size here was large. Crystal size down here was very small. 24-hour filtration time. So you have baffles having no effect on the solid body rotation, baffles having an adverse effect. Okay, and I seriously doubt if this made it into the technical literature. But it's an interesting interaction between flow regime and process desires. When you get the flow regime on your side, that's really fantastic. Anyway, you have solid body rotation, which often draws a center vortex. This is what happens when you have a Fowler retreat blade impeller, except the Fowler will be very large, and you'll have them more or less spin up along the wall. Good place to add powders would be right here, so it gets hit by the impeller right away. It's not. It will be. Could very easily be solid body rotation. Baffles. Who's got the baffles? Just to make some comments. all kinds of different baffles, partitions, bottom baffles. There's a paper by Nagata and somebody. Japanese are very good. Anyway, that paper said bottom baffles help in solid suspension. What I found was just the opposite. The bottom baffles actually hinder. They're trapped various debris in bottom baffles. So anyway, the only baffle here I would really pay attention to is surface baffles. Surface baffles are quite interesting because you can calm the surface down. You can also pump up against the surface baffle. And by having a surface baffle, you may lower aeration. Air is being pulled into the batch. If you have a surface baffle there, you may be able to prevent that air entrainment. Cosmetic industry, they have oftentimes a whole bunch of air being pulled into their processing and in the lotions area, and resulting in long processing times. And I recommend them put in the surface baffle and have it possibly being a floating surface baffle. Of course, you got to worry about that baffle going through the impeller. Anyway, I gave them pictures. It's a great idea for them. Eliminates or reduces significantly the surface aeration, which will lower their processing time significantly, because they were sitting there waiting 2 or 3 days for the gas to come out. The whole idea is you don't put the gas in to begin with. You don't have a procedure that makes problems for you. You have a procedure that doesn't make problems for you. Instead of having a surface baffle, it'd be much smarter to have a process that's neck down at the top, right? To have the wall come in, sort of like one of those bottles you have, large bottles that have necks coming. That way, the whole idea is you process in some place where there is no surface to pull the air in. That wouldn't have the same effect as a surface baffle. So these other baffles are just drawn here just to keep you entertained. No, I'm just kidding. Baffles are not needed in laminar mixing. They're terrible. They become a cleaning issue, and they're not helpful in mixing. In turbulent mixing, you might try a dimpled baffle, so as not to be a cleaning issue in general. So this baffle there's no place where the particles, this is a tank wall, right? Tank wall. And there's no place where the particles can be trapped. Here we got a zone in there that traps the particles and hence becomes a cleaning issue. I was talking to a chap, and he said he didn't care anything about all the things I was talking about. He essentially said all he really cared about was whether he could clean the process. Thought that was kind of amusing. Didn't care about much, just so long as he could clean it easily. There you go. Anyway, baffles should only be used in turbulent flows. Bottom baffles are not recommended. You can even contour the tank for solid suspension and fiber processing. In other words, right below any rotating impeller will be a dead zone. Okay, at the tank bottom. So you put an impeller at the tank bottom, and that will take care of that dead zone. Anyway, N theta, there's been a lot of correlations based upon N theta. It's not a new phenomenon. It's not been named. It can be number of strokes, the number of revolutions. It could be called a homogenization number, all kinds of things. And typically, for an agitated tank, it's T to D to some sort of exponent 1.5 to 2. Number of revolutions to mix. So let's do a quick calculation. K is 5, A is 2, we're at 45 RPM. D over T ratio is 0.3. So what do we got here? Put those all in. We quickly find that This is an exponent. So it's 5 times 3 squared, 9. So we have 45 revolutions. That's not a time sign. That's the exponent that did not get exponented. Anyway, so at 45 RPM, revolutions is 45. So we got it 1 minute. So mixing time's 1 minute. So quickly we find high rotational speeds means low mixing times. Low rotational speeds lead long mixing times. High rotation is not necessary to accomplish mixing. Okay, so you have another experiment I want you to do. I want you to go to the grocery store and get some cake mixes or fudge brownie mixes. In this case, this is Pillsbury hot fudge brownies, and read the procedures for this. Okay, one will say beat, the mix will beat for 40 strokes. Another one would be beat for 2 minutes at high speed with an impeller. Right. So here it's 40 strokes or 60 strokes. Here it is 2 minutes at high speed. Right. Or by hand for 2 minutes. And so all that means right here, high speed for 2 minutes, by hand for 2 minutes, means you have a high speed hand. Just joking here. Anyway, so one is correct, cites revolutions. The other one is telling you time. Okay. So I want you to do this mixing experiment yourself. I want you to mix pancake batter Saturday morning, and I want you to put in five or six phases in pancake batter, right? There's oil, perhaps. There are egg whites and egg yolks, so that's 3. You add powder, and when you add powder, guess what you also add? You add air. So whenever you're adding solid powders to a process, you're probably also incorporating air. Okay. You ever notice when you add sugar to a cup of coffee and you stir it in, that there's a foam layer that's formed at the center after you've done your stirring? And you got to ask yourself, where does that foam come from? Why is there foam on my coffee surface? And then quickly you behold, the foam is created because when you added the sugar, you also added air. I don't know if you're paying attention or not, but you got to be careful exactly what you're adding. Okay. So then you can drink your coffee. But I want you to add the 4 or 5 different ingredients: powder, the eggs, the milk, the oil. Right? Add them all up, and then I want you to beat. I want you to count how many rotations you put in. 1, 2, 3, 4, 5, 6, and see how many revolutions it takes. And I suspect if you count the revolutions, the mixing should be done within 40 revolutions when you're doing it by hand. However, I got to watch out for what type of mixer I'm using and whether I'm not in planetary motion. If I use planetary motion with a wire whip, one of those French wire whips, I can mix fairly well. However, if I'm mixing with a straw, single point straw, it'll take me forever to mix that batch. So again, an example of geometry, importance of geometry. My department head, bless his heart, it was about 25 years ago, he went out and bought a big bag of coffee straws. I don't know if you realize it or not, but coffee straws, where they give you a little straw stirring device. Sometimes at McDonald's, there'll be a little spoon at the end, which is hilarious. And if you stir your coffee with that straw, you ought to feel stupid. No, sorry, didn't mean it that way. You should stir your coffee with a single straw and see how ineffective it is. Okay. Now, my boss, he bought these 2,500 or 5,000 straws. And he comes in and plops it down on the countertop in the coffee room, and he says, "We will never run out of straws." But he didn't realize he said that in front of a mixing expert, i.e. me. So he was thinking one straw at a time. I decided that since was ridiculous and I would be stupid to start, stupid still permitted. Anyway, I'd be dumb if I would use a single straw. So I would use 5 straws at a time, not one, and I would spread them out in a fan fashion. So I would have a large D over T ratio, a large effective D over T ratio. And I didn't have any trouble mixing anything in my coffee with 5 straws in a fan shape as opposed to a single straw. You go ahead and try that, see what happens. It's great. So his 5,000 straws package that he bought didn't last that long. Actually, I never mix anything with my coffee. I prefer it black. But, it lasted, after the word went out on how to properly design mixing it with a straw in a coffee room. The straws didn't last as long as my boss thought it would. Anyway, so here you go. There you go. A mixing principle. Don't mix out. So effective geometry is the number of revolutions fixed by geometry. Mixing is easy if you have an effective geometry. True both for laminar and turbulent. There's a lot of unneeded mixing occurring in industry. Processing can be accomplished by a fixed number of revolutions. That means you need a rotation counter, right? You need a power meter to measure power, and now you need a rotation counter. Okay, this is true for any rotating equipment, extruders, tumblers, grinders, rotary dryers, right? You should look at the various processes. Don't overmix, it's a waste of time. The problem with time is it can be quite meaningless. Anyway, we have a bunch of N theta here for mechanical mixing in. These are all very similar to each other. We have some Japanese, I think there's some Chinese, and we have some Czechoslovakians in there. Anyway, large diameter impellers are effective at reducing mixing times. Of course, they're expensive too. I mean, the helical ribbon's expensive, don't get me wrong. But, if you buy the right equipment, get the job done right. D over T ratio, very important. Laminar mixing, the homogenization number varies from 30 to maybe 300, right? Here's a listing of them. Whereas the 16 up-down mixer is back and forth mixer, or up-down mixer, 16 revolutions and it's mixed. To mix your sugar into coffee, what is it, 2 or 3 revolutions with a spoon, mind you, with a spoon. If you use a plastic straw, it may be several days or not at all, right? So we have the Czechoslovakians, we got the Japanese. Nagata was sensational. Post-war Japan, 1956, he was doing research in mixing far exceeding anything in the United States at the same time. They are really spectacular. Japanese are obviously good at lots and lots of things. Americans, not so much. Americans like to play catch up, which we do very well, by the way. Germans, here's some Germans, the Sigma mixer, the Intermig. The Intermig's an interesting impeller. Notice that we give Reynolds number ranges in here, right? These are probably a wrong way of listing them in terms of Reynolds number. These are classical Reynolds number. What we should be doing is taking the power number defined for turbulent flow, multiplied by the Reynolds number, and that product is the power number for laminar flow. There's different power numbers, one for turbulent flow, one for laminar flow. Laminar flow has viscosity as the major variable. So when they have this statement here of 330, it's really meant to be a statement of power number. Okay. Statement of power number. So power number, power number, power number. It's a little hard to measure power for up-down because it tends to be cyclic. Velocity increases, stops, goes the other way. So the pumping for up-down mixer may be a function of the stroke. And here is our famous, again, Czechoslovakians, universal mixer, problem in the transition regime. This is some of the original diagram from Nagata. Memoirs of the Faculty of Engineering, Kyoto University, 1956. This is sensational stuff. Mixing time times n theta equals a constant. And the Japanese, since they had Nagata, also continually producing good stuff in the area of mixing. This is mixing miscible liquids with different physical properties with a helical ribbon impeller, I suspect. I don't have it here, shame on me. But we have different volumes, volume A to volume B, different viscosity ranges. So we have a whole bunch of different viscosities and different volumes. Up here is another volume, different viscosities. And what they found 3 patterns, this pattern here, that pattern there, and some pattern along here. So they had 3 different patterns. And you can sit there and calculate, this is n theta being 44, excuse me. You have Reynolds number ranges. But the important thing to recognize, they're using a universal mixer, i.e. a helical ribbon. So if I do a band on this, and I tend to be an engineer rather than a scientist, this is 1,000. So anytime when I have revolutions below 1,000 revolutions, I can consider that a well-mixed or a good mixing design. So I go from anything from, say, 50 or 44 up to 1,000 would be a range of good mixing. Anything beyond 1,000, like 10,000, obviously I have a really lousy design and improvements can be made. But, if you're a scientist or if you're really concerned, you worry about what the first mixing pattern was or what your second mixing system pattern was or what the third. But shoot, just ban it, 1,000. So, if you're going forward in life, 1,000 revolutions. If you go back and take your Saturday morning experience and you come up with 40 strokes to mixing your pancake batter, that's pretty doggone good, right? After you finish your pancake batter mixing, I want you to add more milk and see how long it takes to incorporate the milk. And after you incorporate the milk, I want you to add more powder and see how long it takes to mix that. Yes, sir. Good stuff here. So mixing time correlations for jet mixing, right? It's basically mixing time is some sort of volume divided by circulation. Volume divided by volume per time will give you a time. So all these are mixing times as a function of various aspects of geometry. And D is the diameter of the jet, and DO is the average velocity. So some of these are geometry, and some of these are operating conditions. The operating conditions would be to specify the circulation, and the volume would specify the geometry. And if I look through here, we have Fox and Glick with Procter & Gamble. And then we have a Dutch chap, and then we have some Japanese or Chinese, maybe. Then we have Lane and Rice, which is British, and British here as well. So if we get here, we got to understand our jet, right? This is a jet mixing, and we already made some comments about large storage tanks. Jets mixed by entraining surrounding fluids, mixes by entrainment. Most effective are radial jets. You want to avoid walls, parallel to the wall. You do not want to attach the jets to the wall. Jet attachment is not desired. You need it to expand fully. If I'm trying to mix the overall tank. Now, if I'm trying to clean the tank bottom, then I want the jets on the tank bottom. Jets don't mix well in laminar. In fact, they don't exist in laminar flow. Jets do not exist in laminar flow. Jets lasting turbulent flow, 100 jet diameters, I don't know. That's true or not, that's often stated. And you want the entrance jet to be above 200, maybe even higher. But there you go. The important thing is major differences scale up between laminar and turbulent. Turbulent flow, you'll have jet mixing everywhere. in your process. In laminar mixing, however, you will not have jet mixing at all. There's got to be a reason for the mixing. Anyway, continuing on, you do not want procedural mixing. You see this all the time, occurs in procedures with no supporting reasons. Science does not end with the chemistry. Science also carries over into the procedure. There's got to be scientific reasons for different things, not just feel-good times. Add and stir for 30 minutes, 4 hours, 8 hours. 8 hours is typical because that's the workday, maybe for some. Time for procedural mixing is excessive. Should be reduced. Procedural mixing should be based upon a processing need. Time is spent on understanding the chemistry of the process. Time is not spent on understanding the physics of the process. That's very interesting to know. Lots of time is spent on the chemistry, but not a lot of time spent on understanding the physics. Voila, there you go. And up here we have some questions for you. Jets don't mix in laminar flow. And so why don't I'm going to take a quick break here. And okay, let's take a look at more about shear rates, some comments about gas dispersion, solid suspension, liquid dispersion, heat transfer, and chemical reactions. Anyway, the laboratory is typically excellent in the mixing area. Rapid, excellent, designed to provide good mixing, independent of the location. Typically, the laboratory people don't know that poor mixing exists. Plants are notorious for being poorly mixed, can be very slow depending upon location. So when you have effective mixing, you have no effects of method added, no effects of the amount, right? Amount added, no effects of location, no effects of fluid properties. Okay. So if we have ineffective mixing, then there'll be effects of method added, amount of material added, location, and fluid properties. So when I was studying mixing, I had a young daughter, or had young children, and they would have their nursery rhymes. So this is the nursery rhyme I developed for mixing. When mixing is good, it is very, very good. And when mixing is bad, it is very, very bad. Fred once stated, we have found the three most important effects of mixing on our reactors are feed location, feed location, feed location. They were involved with transition mixing for sure. Ineffective mixing can have mixing times go exponential with tank volume. Interesting. That's what we found in our studies. Laminar mixing, it's easy to have poorly mixed. Poor fluid motion, high input, formation of caverns, heat transfer problems. And I gave you an example, basically, of I want you to mix some whipped cream and observe the cavity formation. Laminar mixing is possible to have significant temperature rises due to heating. A viscosity level changes on you, usually lowering, and flow field changes because of heating, which is interesting. We have the fundamental equation, George Klinzik, University of Pittsburgh, way back in 1970s. Great guy. Anyway, he had the equation, the heat transfer plus laminar mixing equals many problems. There you go. Heat transfer and laminar mixing equals many problems. If you cook eggs on the stove, if you don't do surface renewal, don't break up the laminar mixing that might be taking place with the complex egg yolk / egg whites, then you can burn and scorch your eggs. Anyway, as a quick example. Shear rates, there's a velocity change over a distance change. As units of reciprocal time, change in velocity can occur between the impeller and the fluid. right? So these are typically the highest shear rates, the impeller and the fluid. 2 points in the flow. There's typically not the lowest shear rates, but for example, 2 points in a vortex can be high shear rates, but 2 points in the flow often are the lowest shear rates. Okay, depending upon whether there's a vortex there or not. And between the fluid and the wall, there's some high shear rates there. So the wall and the fluid, these are typically thought of as clearances, perhaps, or wall and wall. When the impeller sweeps the wall, you know that the wall velocity is fixed and the speed of the impeller, so you get the shear rate between that gap or in that clearance. Inside vortices and across the fluid at various locations. When we talk about a high shear impeller, it's high shear relative to other impellers, okay? Sort of, one can visually determine which impeller has a higher shear by just looking at the geometry. High shear indicates relatively fast phenomena, right? It has 1 over time to it. And if you flip that, that gives you an estimate of how long things may be happening. Shear rates in the flow are proportional to rotational speed. So average shear rates in the flow might be 10 times the rotational speed. Maximum shear rates is in the vortex might be 300 or 150 times the rotational speed. Shear rates on the impeller, rotating impeller, may be 2,000 the rotational speed. Okay. To give you an idea of the shear rates on the rotating impeller, think about a table saw. You can get very close to that table saw without being harmed, and shear rates are very low. As soon as you touch the table saw, the shear rates go through the roof, right? So I want you to do an experiment for me, a tissue experiment. Basically, I want you to hold a tissue out the window. And if you hold the tissue out the window at 60 miles an hour, it doesn't take long for the shear rates to destroy the tissue, right? So that would be sort of like a wall-bounded shear rates. Anything that has a wall, okay, or a solid surface. And then same experiment, the tissue shredded the first time. Then I want you to put the tissue out, and I'll let go of the tissue, and you'll find that the tissue goes up in the air and back down again. Anyway, but it isn't ripped apart. So if you're trying to disintegrate stuff or have increased surface area, you got to get near the impeller or get into these vortices. If you go and take high-speed motion pictures of, say, grinding in a mixer, you have a flat plate there, and the particle approaches the flat plate. You can see the particle all the way down until it touches the flat plate, and it will touch the flat plate, the rotating plate, and it disintegrates. Next frame, it won't be there. So it's kind of interesting. So you're very much interested in the surface renewal on the surfaces. In other words, if I was to feed a system that wanted the particle disintegration, I would make sure to try to put the feed directly onto the rotating surface. Okay. So I'll just go on. We talked a little bit about gas dispersion, a little bit about solid suspension, a little bit about liquid-liquid, and end with heat transfer and chemical reactions. Anyway, we look at gas-liquid mass transfer. It depended very much upon surface area. I contend that there's 3 regimes: a gas-sparged regime, mechanically agitated regime where the impeller disperses the gas, and a choked regime. Choke regime is not very well talked about, but not very clearly understood. Things can't go on forever. Impeller can break down only so much to a certain size and can only handle so much gas. So the mass transfer coefficient should be determined by the process under consideration. Let's take a look at this. This is by John Smith, Van Reet, Klaus Van Reet, and John Middleton. Great guys. Admire them greatly. You have the mass transfer coefficient versus power per volume here. This is gas power per volume. And you have the gas sparged regime, which is over here, where the superficial gas velocity is an important variable, right? Gas sparging contributes power. It's a power source. And that power source generates a mass transfer coefficient, KLA. Then you have agitated area, and here you have two different tank diameters. Impeller rotational speed is important, so you're going higher up here, right? And agitated tank, okay? So this is the impeller addition to the KLA. And you see gas sparging contributes very little, whereas this contributes factor 5, 10 times, 20 times more than the gas sparging. So between these two, the gas sparging doesn't do much. It's the addition of the power from the impeller, that, or the gas power, I should say. We got to be careful what that actually is, and contributing to higher KLA. Now, what further on happens on this, you notice this is sort of tipping over. Anyway, at that region up here, you start to enter a region where the impeller becomes gas choked on the gas. There's not any power to disperse the vast quantities of gas. So, in a sense, the impeller is not choked. It's not flooded, but it just can't handle any more gas. And basically, choke flow conditions sit up here, which I talk about. It's a gas band sometimes. You take a Coca-Cola bottle, fill it up with water, turn it upside down, and you have choke flow conditions. Before the water can come out of the Coke bottle, air has to go in. So air goes in, water comes out, air goes in, water comes out. And it's under a choke flow condition, and there's only so much mass flow rate that can come out. If you take a glass of water and pour it, water comes directly on out, no problem. But with gas sparge systems, you can reach a choke condition where you have the flow being somewhat maximized. Since the flow is maximized, you reach a maximum in KLA. This is a great plot by Sitar and Potter following Counterblank's work, some original work from Counterblank. This is excellent. This is a repeat. Interfacial area as a function of this parameter here. I would spend a lot of time, if I was in the interfacial area business, spending a lot of time figuring out what the various parameters of this thing is. You have gas power. You have gas power, and then you have the total power sitting here. That's good. I think that's total power. Anyway, this is apparently an excellent correlation. It happens to be followed in England with Counterblank, and these chaps are in Australia, and so it occurs in Australia as well. So you assume if it occurs in England and Australia, then, well, anyway. Impeller design, obviously, you need a disc, first thing. Need a horizontal disc, forces the gas into the impeller. Very high gassing rates. The process becomes opaque, and the impeller is buried into a foaming gas band. Now, gas handling capability depends upon the impeller blade number. More blades, more capability, and shape of the impeller blade should be cupped in the direction of rotation. Now, I studied this. I've been preaching this an awful lot over the years. More impeller blades, the better. So I did a study changing the blade number from 6 to 12 to 16 with this new technology of 3D printing. I printed up myself some impellers, and I got a graduate student. And more blades do increase the performance up to a certain point. and the exponent on more blade number is 0.4. So whatever the blade number is, or from the original design, I go up. Blade number, the effect ratio-wise will be 0.4 exponent, which is not 1. It's not proportional to blade number, but it is affected by blade number to a 0.4 power. Again, the idea of the Smith impeller, if it's just a flat blade, instead of rounded here, flat blade, you have vortex at the top, vortex at the bottom. They fill in with a gas and they form and converge here to a large gas cavity. That reduces the dispersion capability of the impeller and it becomes, quote, flooded. And the aeration number power drops to 0.4, I think, roughly. And the aeration number is not very high, 0.04 on the aeration number. Anyway, you go to a hollow blade or a curved blade or a pipe blade impeller, you have the vortex sitting here and you have the vortex sitting here. But you don't allow the vortices to meet because there's I suspect, a high-speed jet right here. Right? Remember, the direction of rotation is going from right to left. Right? So these are high dispersing impellers. So the aeration number to go from, instead of 0.04, could go up to 1, 2. Got to figure out what I mean by the aeration number. Basically, aeration number is the handling capacity, the amount of gas being handled by the impeller, which is volumetric flow rate, divided by the pumping of the impeller, or ND cubed. You got to watch out for D's in there. Anyway, the idea, increased blade number on the impeller will increase the disperse effectiveness. Vortices are proportional blade number, increased blade area, increased shear rate, blade geometry, and angle effects intensity. Anyway, did we get this one? Smith impeller should not be used upside down. That's very important because when you flip that sucker, you have always have to stop and think about that, whether it actually is true or not. If I flip this thing, right, and mount it, I got to mount it, I get the wrong mounting. Anyway, I got to watch out. It's always cupped in the direction of rotation. It's something that you got to check for. I like maintenance people, but they can change your process. Okay. By the way, a lot of the impellers used in fermentation batches, you still use the Rushton impeller and 2 pumping impellers. It would be a smart move if they have 3 of the Smiths. In other words, at the bottom of the tank is usually a flat blade impeller, a Rushton. They should replace it with a Smith. Halfway up, they have, or a third of the way up, they may have a pumping impeller, hydrofoil. You should replace that with a Smith. And the top impeller should be replaced with a Smith. The idea would be that you gas sparged each one of those. Right at the present time, fermenters are gas sparged to the Rushton impeller on the tank bottom, and the other 2 are pumping impellers. That's not necessarily a good design. Better design would be 3 Smiths where you gas sparged each one of those. Same thing for chemical reactors. Solid suspension, well, solids are a first-class pain in the neck if you haven't figured it out. The research on solid suspension tends to be varied. It's not easy to get agreement. And possibly you can see why solids are not as easy as gas. Gas liquid solids are much more diverse phase. You got particle shape, you have particle size, you have a non-movable interface. I mean, the solid interface is not going to change on you. You potentially have 7 different surface chemistries, and the idea that surfaces are actually trash collectors. Okay. And you don't really know what's on the surface. You don't know where the surface has been, what sort of poisons it's picked up, what sort of material has been coated on the surface. You don't know the effect of moisture content, oxide layer, or whether it's hydrated. So what can I say about solids? Solids is a problem phase. You want problems? work in the solids area. Right. Goal is to get surface area exposed to processing. So you want to test for particle size, obviously. But do you ever mention particle concentration? Okay. Case in point, you can tell me the size of a Cheerio, but I seriously doubt if you can tell me the concentration of Cheerios in a box of Cheerios. How many Cheerios are there per square inch, cubic inch? Then the other kicker is, since solids are a trash collector, surfaces are trash collectors, have you tested for solids freshness? It's not uncommon to have a grinder in a reactor, right? Freshness is rarely studied. In fact, there's a study where a catalyst was being used. Enough was ground up for 3-day use, so they used the first day, second day, third day. Over the second and third day, the catalyst surface became oxidized and the effectiveness dropped as a function of age. Right. So if we continue on here, we divide solids up into two categories, simple solids and complex solids. Complex solids you need to read or listen to my audio or my video recording on agglomeration. Right. So complex solids depend upon particle surface chemistry, process-specific agglomeration is a major factor. So we have simple solids is sand without any moisture. Very little effect of surface chemistry. Free-flowing, right? Follows the Zeiderine correlation, 1956. Basically, the idea for solid suspension is that these free-flowing solids stay on the tank bottom less than 1 second. Suspension is easily accomplished, and suspension becomes similar to blending. It's kind of interesting. So we have the Zeiderine correlation. It looks like this. However, Zeiderine should pay attention to the slope here. Zeiderine correlation has the effect of solids concentration, I think 0.13 power. Right, but up here, the slope might be, with heavy suspensions, the slope of particle concentration may be 0.5 exponent. So we have the condition of solid suspension here, and here when the impeller is buried into the solids, and then we have solid-solid reactions or agglomeration going on, all bets are off. So solids is a really difficult area to work in. Even sand becomes non-free flowing. If I take sand on the beach and I make castles with wet sand, obviously sand is not free flowing. However, because of the moisture content. However, dry sand is free flowing. And we have this very famous work here. Generally speaking, with homogeneity, with solid suspension, there's a claim that there's always some small layer of clear liquid up here. That's not true. They topped it out at 0.95, thinking that there is always going to be some clear layer at the surface. That's not true, right? If I pump up to the surface and have a rolling surface up here, the surface concentration of solids will be what was pumped up to it. So generally speaking, however, whenever you deal with solid suspension, there is a gigantic clear layer. If I have complete homogeneity, that will disappear, and I'll have solids throughout the entire tank. So this is a good group of guys here. They work for Shell, I think, Royal Dutch Shell. I'm not sure exactly. These are Dutch names, so I won't brutalize them with my poor pronunciation skills. But they have the modified Froude number, which is basically from Zeiderine's correlation or Zeiderine's work. Very good group of people. You have the Z over T plotted here, and the Z is how far up the cloud will go. And typically, you calculate the modified Froude number, and you can see how much the suspension will obtain in the tank, or how big this clear layer is. This is a first-class pain in the neck when you're looking for complete homogeneity. As I'll say a little later, if I'm looking for uniform distribution of solids, like I would in dispersing radioactive material in glass, I want complete homogeneity. If I'm dealing with paints, I want complete homogeneity. And even if I have the drug manufacturing, I want complete homogeneity. In other words, I don't want two reactors. This is one reactor, and this is another reactor, and I actually have two different sets of reaction conditions sitting in here. So now, that ain't true, Tatterson. Well, if your kinetics are quite complicated, it is true. Okay. Up here, there's no solids, so the reaction kinetics is different than down here where there are solids, i.e. this has a catalyst perhaps. This doesn't. This presents one set of chemistries, and this presents another set of chemistries. And go ahead, don't believe me. Anyway, my friends at Merck say they never run this way. Excuse me, I apologize for using Merck. Nice company. I like the company greatly. Admire the company, admire their personnel and everything. Anyway, sorry. They run flat out, complete homogeneity, so they don't have any mixing effects on their reaction products. Case in point. So, run very famous mining company sued another very famous mixing company, and I was involved with the lawsuit. It was pretty funny. Every couple of months, I get this phone call from this company, and yeah, I'm still available. Yep, I'm still available. I got to take a trip to Brazil. Now that made me stop and say, Anyway, I had to reanalyze whether I was going to Brazil or not. The jungles of Brazil, and there was a yellow fever outbreak. So Anyway, what happened was this fantastic. Lightning came through like a bunch of champs. It really came through. Basically, what they did, they had this situation. They were being sued because they had to. How can I say this? The original design called for complete homogeneity in this tank, right? Complete homogeneity in this tank. And they delivered this situation here on this graph. And I went through the calculations, and lo and behold, this holds true. This stuff is pretty good to what was actually measured. Anyway, so I did a whole series of calculations on that. Didn't get paid, but that's okay. I got to keep the videotapes. It's a nice exchange. I have the videotapes. I didn't get paid, and the company got what they wanted, and Lightning delivered spectacularly. So you got winners in all around here. Anyway, so John Van Nessen, who used to work for Philadelphia Mixers a long, long time ago, and I suspect he's gone. He was cankerous guy. Anyway, he said what you do is you draw the flow field you want. In your processing, you sit down and draw your flow field. And then you come along and put the impellers where that would deliver that flow field. And he said that was a design procedure. I thought that was pretty cool. John Van Nessen with Philadelphia Mixers. He, tough customer. I mean, he's man of the world for sure. He one time showed up wearing his straw hat and his beach flip-flops and a bathing suit to a mixing conference. I thought it was great. Anyway, so what Lightning did is, I hate to say this, but may have followed John Van Nessen's lead and put an impeller up here, a smaller diameter impeller. So, and the pumping direction, they would have it pump upward. So the bottom impeller would pump along and reach the upper impeller, which would take it all the way to the tank, tank surface, right? So you have a down pumper that sweeps the bottom of the tank, sweeps it up to the up pumper here, and pumps it up. Now, since we're dealing, you don't really have to necessarily change the motor, and you don't have to necessarily change the diameter of the impeller, but I suspect they did. Anyway, they can add a second impeller up here with no real hit to power draw. The impeller, a smaller diameter, powers D to the fifth. So if I have a small diameter impeller up here pumping to the surface, that's okay because this impeller is the dominant power draw. So this is D to the fifth. Up here, this is D to the fifth. But this may be 0.6 the diameter of that impeller. So there you go. That was a sensational design. I actually know who did it inside the corporation. So anyway, I was rather impressed with that. Don't run across excellent design all that much. Complete homogeneity is usually not needed, which is quite true. All you're interested in getting the solids off the tank bottom exposed to processing. And once you get the solids suspended, it doesn't matter how far they go up into the tank. However, some processes like paints and radioactive sludges and drugs, you want complete homogeneity. And this usually in the olden days would require 4 to 10 times what off-bottom suspension would be in the way of power. Power would be a high input. However, again, this concept of getting rid of geometric similarity and change the geometry, you can get a significant advantage. Again, one down pumping impeller on the tank bottom and the other up pumping impeller 1/3 from the tank top. So one impeller lifts the solids off the bottom, the other impeller carries the material throughout the liquid. Fantastic geometry, very impressive. Solids is a common problem in industry. Common problem to help prevent solids is having an impeller on the tank bottom. A very common process objective is do not lose suspension. Prevention of suspension loss requires a review of the processing cycles. Settled solids is not a simple matter. Permits solid-solid reactions to occur, i.e. agglomeration. Resuspension may be a major problem. You may have a new tank bottom. Solid-solid reactions cause strong bonding, and startup torque is going to be higher. Remember, we were talking about the spring impeller buried in clay, in the clay industry. That was in Georgia. Anyway, liquid contacting. Area generation is controlled by the impeller. Area destruction occurs in the bulk of the tank. So you have generation, destruction going on. Basically, you have these trailing vortices. And if I take a look, it explains a lot here. We have a Rushton impeller, or a distal impeller. We have a drop going over this blade. It doesn't break up as it goes over the blade. It's large enough that there's very little breakage going on. If it was smaller, it still would be no breakage. And so it participates in this high-speed jet between the vortices, but then it sees the vortices. Here you have a little curl up as it starts to enter the vortices, entering the vortices even further, right? And then eventually you got dispersion down here. It's pretty. This is a picture that I drew. There's a dispersion sequence. So what this tells me is the more vortices I have, the more high-speed jets I have, the more dispersion I will get. Again, the 0.4 power. Going back to this, well, let's see. Where was I here? Here we go. So drops flowing over the blade, 10% of the time they'll break up. How do I know that? Well, I counted the number of drops breaking up. The true breakage or dispersion occurs in the vortices and the high-speed jet. and it's sort of the flow hits a brick wall. The brick wall is called the bulk of the tank. Now, in the bulk of the tank, you have drop coalescence. So you have a fight between drop coalescence and drop breakage. So you have to have a balance going on. And again, you have different process objectives. We have the idea of making emulsions, making uniform drops, having high surface area, which might be quite different than having high surface area with coalescence. Right, emulsions, the drops become solid-like and don't coalesce, so your surface tension is going to be controlling. May carry an electrostatic charge, the charge on the surface. Again, uniform drops can be made by simple disks with all the material seeing the same flow field. I was visiting a very, very nice company. They had me in, appreciate it. One chap said, well, how do you make uniform drops? Now then, I remembered at the time that there was this spinning electrode in electrochemistry business. In the spinning electrode, they had calculated the flow field, and the flow field consisted of a series of roll vortices all around the surface area of these disks, and the roll vortices were all uniform. So one way of making uniformity is to start with a uniform flow field. So when a drop would enter these vortices, they would come out, they would experience the same flow field and come out. And remember, if I have a tank, right, I have drops being produced around the impeller region, by the way I was showing you. Then way out in the tank here, I have just dead zones where large globs of stuff reside, right? And they might go into the pump and get dispersed again, or they might go through this nozzle and get dispersed again. But the tank is destroying so in my tank, I have huge heterogeneity, huge amounts of heterogeneity sitting in the tank. Whereas around the impeller with these discs, I was producing very uniform drops. So what I want to do is produce very uniform drops, and then I want to take them out of the tank really quickly. Right? I don't want to let them discharge in this tank where there's large homogeneity. So it's a matter of making the stuff and then taking it out somewhere else. Or I would have this as an inline mixer of some sort. Anyway, where was I? Anyway, uniform drops made by simple disks. All the material sees the same flow field. I have these vortices here. I still have my high-speed jet, so I may have some disruption of drops in here. And I don't know exactly how drops will deform with these vortices. Hopefully, there's still this high-speed jet here, which I suspect it probably will be. So I'm looking at increased blade number. That effect is 0.4 power. The idea is vortices proportional to blade number. I'm interested in blade area, shear rates. Anyway, is blade number increased on scale up? I hope so. Right? Think about a 4-inch diameter impeller with 6 blades. Now, there you go. It's nice. Or maybe 6-inch impeller with 6 blades. That seems reasonable. But stop to think about it. I scale up to a 3-foot diameter impeller and I still have 6 blades. My question would be, are you nuts? So blade number will increase. Spacing distance would be, the minimum spacing distance should be twice the blade width, right? I have this blade width, the next blade should be 2 blade widths down, that even more than that. But I certainly, with a larger diameter disc here, I would certainly increase the blade number. I was at a pharmaceutical company and I talking away, and I said, how many impeller blades do you have on this disperser you have? And the answer was, did you hear that answer? I asked again later on that day, I said, How many blades do you have on that disperser? The answer was, did you hear the answer? Anyway, when I was leaving, the guy was nice to me. I asked how many blades. He said 27. Well, I don't know if 27 is real or not, but you obviously I have to have the blades separated enough so one blade flow field does not enter or affect the other blade flow field. But you can't have them, so that would give you a minimum separation distance. You can't have them blade, 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 blade. That would be ridiculous. So I've seen people have the blades very close together. Maybe. I mean, that pumping has to go somewhere. But I suspect that these vortices may not form. And the high-speed jet is reduced. So again, these blade spacings, you can see how far they are. This jet, or this phenomena here, is the blade has moved on, right? So, right, this blade is this blade is this blade, and this blade's moving on. So there is some separation distance between this jet here and that blade. And certainly this material is getting very close to this blade coming on. So there you go. Blade number, well, don't know the effectiveness of the Smith impeller and liquid-liquid processes. Not a great improvement. Of course, we have our famous question here, where's the emulsion being produced, right? So the emulsion, remember this impeller is what, 500, maybe 300 RPM? This pump is going around at 1700 RPM or 3600 RPM. So I may want to do all kinds of stuff with that pump, see if that's affecting my emulsion. Heat transfer. Oh, yes, heat transfer. Quality and proper operation are closely related to heat transfer. Lots of processes are heat transfer control processes. Examples: cooling, caking, cooking, melting, freezing, crystallization. Heat transfer is assumed to be similar. Heat transfer in a boundary layer. Okay. That means heat transfer correlations that you have for boundary layers, which are used for agitated tanks. Well, you typically have a big difference because in heat transfer in agitated tanks, you have a D over T ratio that has to be accounted for. You're looking for good fluid motion, good circulation in the bulk. You're looking for good exchange at the heat transfer, eliminate hot and cold spots. Scale up the issue with heat transfer, dead zones form, lower heat transfer coefficients. The prediction of heat transfer coefficients is difficult. Fouling also increases, right? So you have the famous equation by George Klinzig, University of Pittsburgh, nice guy, really like him a lot. Laminar flow plus heat transfer equals many problems. Poor liquid mixing, material may burn, heating elements overheat. You may need scrape walls, scrape wall equipment. Oh, geez, I never heard of scrape wall equipment. You use scrape wall equipment all the time in the kitchen. Whenever you have heat transfer, hopefully you're using, when you're cooking your food, hopefully you're using a flat spatula, right, to scrape the wall, the pan, the bottom of the pan, keep your food from burning. So one of the interesting things about process physics is the physics in the kitchen is the same as the physics in your plant. I thought that was pretty fun. Right. Let's step back a second or two. Okay. This is a story. Anyway, they have processing, right? They have powder sitting in here. You have an agitated tank. It's a helical ribbon. You have splash up. Now, the splash up was not taken care of. So the splash up got reincorporated into the batch basically, and that reincorporation left that particular chunk of material fairly well unmixed, and it went on to cause quality problems. However, splash up in the kitchen is a common occurrence when you're making, when you have a mixer in there and you have stuff clinging to the wall, and typically you wipe it down with a spatula incorporated in the batch here. So that's the idea of what occurs in the kitchen often occurs in your plant. Anyway, so let's see what we got. Heat transfer. Laminar flow plus heat transfer needs scrape wall equipment. I mean, an extruder, if you take a look at the scale up of an extruder, they scale up 1 to 2 or 1 to 4. You know, they don't scale up huge amounts in sizes, right? Heat transfer coefficients are easily measured or monitored. It tells you when to perhaps clean your tanks. Also used as a diagnostic method for your process. Your mother or your father measured your temperature while you were sick. The same idea as you're measuring temperature of your process with heat transfer, understanding your process with heat transfer measurements. Chemical reactors. It is amazing how sophisticated we are and how little or how poor reactor design is actually done. I thought it was quite interesting how advanced we are. And at some point, perfectly black mixed and plug flow reactors are going to be hopefully replaced by better determination of what the physics is actually occurring in your process. There's nothing wrong with those as being the baseline. And again, they should be taught, right? But they should not be taken as simple. That's all there is, because there's a whole bunch more. Okay, reaction. For a reaction, you got to bring the reactants together. And without the mixing and contacting, there is no reaction. Reaction. You want to have the desired product, maximize the product, minimize operating recycle costs. Okay. Minimize impurities and separation costs, minimize safety, environmental issues. When I was taking organic chemistry, the professor said it reacts this way and doesn't react the other way. I didn't quite understand why. He said it only reacts this way, it doesn't react the other way, as you've mentioned. I didn't believe him. Basically, I thought it's potentially possible to react this way or that way. So whenever you have a reaction, you got a whole soup of stuff, right? He went on, the organic chemistry professor, he went on to Washington, D.C. and became a bureaucrat. Hey, that's okay with me. I since learned that these side reactions, which I asked, he told me they didn't exist, do exist. And one of the goals is to prevent side reactions, okay, and minimize safety environmental concerns, maximize one reaction, minimize the rest, okay, minimize side reactions. Design approach is design and geometry and operation based upon the kinetics, not the reverse, where you force the kinetics into a fixed reactor. In other words, you look at the reaction scheme, and there will be more than one reaction, and they may be one reactor is preferred over another reaction. So you're looking to maximize one reaction, and you got the other kinetics happening, and maybe you have a secondary reaction or you have a reaction sequence. So what you want to do is look at the kinetics and see which reaction you want to minimize, which reactions you want to minimize, and which reactions you want to maximize. And then you design the contacting to match how you're going to add the material together, how you're going to separate the material. So you're much more attuned to matching the kinetics to the processes, right? You just don't force it into a single reactor, stirred tank reactor, and hope for the best. That's not a good way of doing reactor design. Right. So what is it that we want? Well, first big question is reaction. Where does the reaction take place? How fast is that reaction? Now, I always like to point this out. The volume of the reactor is not the volume of the reaction. I sat there through reaction kinetics with Dr. Liu at the University of Pittsburgh when I was 21 years old. And, I didn't believe it then. Anyway, most reactions are multi-phase. Aha, right? Fluid mechanics and contacting phase becomes important. So if we take a standard reaction up here, we have what I would consider my standard reaction, a reactor, whereas I have a feed plume here. Now then, the reaction could be at the surface area of that feed plume. Okay? There's nothing that says it can't be there. Or even worse, that it reacts back up the pipe, where the reaction rate is faster than the feed. So you have back reaction up the feed pipe. That is really dangerous, right? That's why the Japanese lost World War II in the Pacific. They had all these gasoline tanks, all these gasoline lines sitting on the top surface of their aircraft carriers, and they didn't back purge the gasoline out of these feed pipes. And so when the bombs of the U.S. or whoever, the Navy, bombed the surface of these aircraft carriers, the gasoline lines back reacted to the gasoline storage tank. So in a matter of 3 or 4 bombs, the aircraft carrier exploded, or it was severely damaged. And that's quite right. And these you watch the aerial videos on YouTube History Channel and watch how long it took for when the attack of the American planes on a Japanese aircraft carrier, how long it took for the aircraft carrier to suffer significant damage. And it was 5 minutes. It was quite rapid. Again, you hit a feed line, go back to the storage tank. That's not a good thing to happen, right? Of course, I've run into chemical companies that said their feed comes in and exits right away. Doesn't see the bulk of this tank. That happens as well. What can I say? Example of that would be backfires on a car. The gasoline goes into the engine, does not react, exits the engine, and then in the muffler area or whatever, it catches fire and you have a backfire. So this business about feed, you got to pay attention to things a little bit. Back reactions are very possible. Again, Japanese aircraft carriers. Feed coming in and leaving, major specialty chemical company, no longer existing. Then the C here, a standard procedure might be feed before a pump. That means the reaction may actually take place in this pump. It's called a pump. It's not called a reactor. Feed reacts in the pump. So this is a pump reactor. Or the name pump's got to be changed out with some recognition that this may be a reactor. Or you have reaction all the way up along this feed line, or you have a spray nozzle up here where it bursts forth. Okay, continuing on. So we have a lot of interesting things happening here. It just didn't quite make the textbooks. You know what I mean? How about catalyst surfaces? So the surface of the catalyst exposed to processing depends upon, what do you call it? The solid suspension stuff. The chaps at Royal Dutch Shell, which I showed you the Z over T ratio. Now that will give you some idea of how much catalyst surface is available for processing. Now, if I want that catalyst to go throughout the entire tank, I would have a bottom impeller sweeping And then I have an up pumper sweeping, right? Sweeping up to the surface. So I have the catalyst throughout the entire tank. So then I would worry about the concentration of solids particle, which I may or may not know for sure. I would worry about the catalyst freshness surface, which I don't know for sure, and among other things. And if it's multi-phase, I got to worry about whether the particles are picking up another phase, because solids are a trash collector. Bubbles could adhere to the solid. Liquid drops can adhere to the solid. So I got all kinds of processing problems with that that solid phase. Then I have gas bubbles, which brings up a whole slew of things about whether there's a gas band around the impeller. And about the gas band, you got to go study my scale up course. Then I have in there liquid drops. Now I got to worry about whether there's zones in this tank where massive coalescence occurs, i.e., around the upper corners and between the heating coils here, whether there's not dead zones in there where these these small drops are coalescing. And I don't quite know the surface area of those drops, although I could use a counter blank Potter correlate, Sitar and Potter / counter blank correlation to tell me the interfacial area. Okay. Now I may have a bank of heating or cooling coils in there, right? And if I have an endothermic reaction where I actually have to put in heat, the reaction will be around the heating coils, because that's where the heat is. It's an endothermic reaction. The rest of the tank is dead zone. Okay. reaction. Where is the reaction? That's funny. You think we know stuff? There's many chemical company that certainly does not understand completely their reactors. There's always rooms for understanding even further. I like this. You have this pump around loop where you have spray coming in at the top. Maybe the spray then pulls in the head gas, and the head gas is necessary to kick off the reaction. So then I would worry about the spray up here. Of course, then again, I could throw in the issue that now it's gotten so hot, the only way to cool down this system is have it run boiling. So now I have a boiling reactor, it's sparging gas at the same time. That's pretty neat. Or say I have a boiling system with liquid drop dispersion or solid suspension going on. So, I don't know if any of these reactors exist, but I assure you, it's within the realm of possibilities. What I like to do someday, if I was younger, you have all these specialty chemical suppliers. So you have specialty chemical suppliers where they make this compound and they make that compound and they make this every compound. I suspect they're real champions at designing reactors, because they got all this different stuff that they have. And you want to write a reaction book? Go talk to those guys. They should write a reaction book. But they don't want to write the reaction book because it would give away their technologies, right? So if I was a chemical engineer, I'd try to get a job with those guys and learn a lot about chemical reaction if I was a 22-year-old free and footloose. So chemical reaction is not as simple as plug flow, not as simple as CSTR, not as simple at all. Scale up of this feed plume, I would worry about the surface area of the feed plume. Scale up of this endothermic reaction, I would worry about the evaporation of this feed. And also I would worry about surface area of this heating coil. If I had surface reactions on the catalyst surface or the bubble or the drop. So all kinds of things to worry about. Reaction, where's the reaction? So I'm going to have a reaction throughout the homogeneous matter, heterogeneous feed pump, up the feed pipe, feed plume, heat transfer surface. It was pretty funny. I knew of one process, radioactive material. Basically, it had a line going from one plant to another plant, and it was radioactive material, basically. So they had the valve closed and an empty line, another valve. And what happened, somehow, this valve on one end containing the radioactive material somehow got open, and the reactive material came all the way up and was at the next plant before they knew it. Steam lines condensing in the winter. Anyway, reaction, where's the reaction? This is only a partial list of the reaction zones. Boiling surface, walls of the tank. That's why you put glass on walls. Surface to volume, right? Solid catalyst. Surface of solids or catalyst particles. Surface volume, surrounding bubbles and drops. Interfaces between two large volumes, that can happen. Spray volume, drop size, header gas coming in, setting off the reaction perhaps. Drop surface area of a spray, all kinds of places. Reaction, where's the reaction? 93. The chemical reactor is not performing well. You need to look at the contacting or the mixing. It's been my experience that chemists are extremely competent, right? Their chemistry is usually very well thought out. So we have Doug Ling at, I won't tell you the company, but it's a big company. Basically, they had small scale, large scale, and large scale, they didn't have the same flow conditions. So Doug Ling recognized that, comes in, changed feed locations, and voila. He turned around the reactor. Everybody was pleased. Think of what that does to your reputation. You walk in, you say, move this pipe over here, a couple feet, and suddenly the reactor turns around and performs quite well. Changing feed locations, standard technique in my business. And just think, you sort of like, right out of the blue, change feed locations, everything is wonderful. You may want to design your reactor as a contactor, maybe a heat exchanger. It's not if you have a large exothermic reaction, right, you got to get the heat out. And there's several ways of doing that. One, you run boiling. Small scale, you didn't boil. Large scale, you boil. Another way is fill the whole reactor with a heat exchanger surface. Fused metal spheres, conduction out of a metal sphere bundle, fused together, might help, or a combination of both. You may wish to mix fast, react fast, and separate fast. Actually, you ought to run all your reactions assuming that there is an intermediate. If you run fast, mix fast, catch the intermediate, then you want to stop. You want to examine what the intermediate was. Sort of like undiscovered gold. Mix fast, separate, stop the reaction, see what you got. It will be a costly experiment, but there's a lot of reactions that take place in 2 days, right? However, there are some reactions that are practically instantaneous, right? And produce something, and that something then reacts slower to make something else. So you catch that intermediate. It's a matter of timing, right? They also ought to include timing in chemical reactions. These intermediates can be quite valuable. Right. So oftentimes you may mix fast, which is not a CSTR, right? It might be static mixer, react fast, and then you want to separate fast. See if you can discover intermediates. Or instead of separate fast, well, this is separation. After the reaction fast, you want to hide the product. You want to flash it off, freeze it, extract it, crystallize it. Right. Some of the tricks involved with doing the test reaction going on. Again, these guys making all these specialty chemicals, I'm sure they have a lot of tricks up their sleeve. Technology that right might help you. And typically, you hide the product. Add dropwise with good stirring. Now, there you go. My uncle Gene Haley was involved. He was an organic chemist, notoriously bright guy, right? And he participated in a number of explosions. Anyway, he had, in his old age, he had pieces of glass come out of his face because that's where they went when he had these different explosions. Anyway, add dropwise with good stirring. He didn't quite understand, or he did, and he didn't tell me. I expect that was true. He understood, but he wasn't sharing. Anyway, add dropwise with good stirring. That mixing effects are going to be present. So this whole business about reactor design is, it's time to make a step forward a little bit. Maybe we shouldn't, given the political situations we're encountering these days. But I guarantee you those specialty chemical suppliers are got a whole slew of tricks up their sleeves. Anyway, we leave you with this. Process failure. It's need for another type of equipment, need for another processing strategy, need for changing process objectives. I've never failed at anything. I just changed the process objectives, right? So we have Dilbert here. You haven't heard what the problem is yet. How can you recommend building a database to solve it? We always build a database. Well, we'll need coffee mugs for the team project. The problem is we have poor processes. That could be the slogan on our coffee mugs. Oh boy, that really hits home, right? Yes, sir. Anyway, I leave you with some questions. No, don't bother that. These books, Process Design, these are good books available. They're inexpensive you can buy them used though. No problem. I don't get any money from them. Let's put it like this. The money I get from these books and $5 will get me a cup of coffee at Starbucks. Anyway, happy mixing and contacting to you. Thank you for participating. This is not my phone number. I am probably retiring. This is now February 18th. This will probably be my last semester, 2020, sorry. February 18th, 2020. This will be my last semester at A&T. I'm leaving the mothership, and I'm giving this stuff away, and I hope you will enjoy it and take it to heart. I have a whole series of other videos, but the mixing was my first love, so to speak. And I hope I've contributed to the knowledge of mixing. And I am available for consulting. Anyway, you all take care and have a happy life.